So, good morning, everybody. It's my pleasure to have here today Professor David Wales from University of Cambridge, and he's going to talk about exploring energy landscape from molecules to nanodevices. Thank you.
Good morning. It feels like you're all very far away. So before I start, I would quite like to know where you're all from. So not individually, we'll do a show of hands. Who's from Switzerland? Come on, somebody's from Switzerland. Who's from Italy? Yeah. Germany? France? England? Come on, John. Right, so, and I was told it was a very heterogeneous audience, so there are a couple of places where we can do different things, and I'll ask you when we get there, so pay attention, because you'll either get a load more equations or more applications, and I will go with whatever you like. But this is my topic. Can you see the pointer? It's a bit faint. So I'm going to talk about exploring energy landscapes, and our philosophy here is to try and compute and understand things from the potential energy landscape. Now, here I'm coarse graining automatically in terms of local minima and transition states that connect them. And we use this as both a computational and a conceptual tool, a way to think about things and a way to do calculations. It's a bit different from conventional simulations. And we'll come back to that in the afternoon with the hands-on demonstrations. There are three main aspects to this exploration. One is structure prediction from global optimization, where we use basin hopping. I will show you some examples. One is enhanced sampling for thermodynamic properties, and here we're going to use basin sampling. This addresses the broken ergodicity problem. And then if we want kinetics, I'm going to talk about discrete path sampling for rare event dynamics. But the key point is that whatever system I'm doing, I'm using the same methodology. So whether we're doing small molecules like water clusters at a high level of accuracy with explicit consideration of electronic structure, or whether we're doing very coarse-grained modeling of a colloid or a protein at an intermediate atomistic level of detail, I'm doing the same things. I'm calculating stationary points and the pathways that connect them. And for small systems, we can find all the transition states that we want, and for large ones, it becomes a sampling problem. So a small system would be something like a water cluster. So here's water trimer, and this is the flip rearrangement, which we can treat at CCSDT level of accuracy, if you like. It produces large tunneling splittings in experiments, and I'll come back to a landscape for one of these water clusters. I'll do the dimer and the trimer later on to break up some of the equations. And then at a very different level of detail, this is a representation of 600 colloids on a liquid-liquid capillary bridge. And it's colored blue to red from top to bottom. And it's a pathway between two different defect motifs, where we have an extremely coarse-grained model of the whole system. So as Dan Frenkel, world expert on colloids, says, everything we know about colloids we know from coarse graining. And if you have a quick look, you can see that some of these rearrangements are very localized, some are actually delocalized with chains of atoms moving. There's no reaction coordinate. You couldn't possibly guess how the system goes from one place to another. So you actually have to calculate the pathways in all degrees of freedom, no projection allowed. Nature is stranger than we can imagine here, and there's no substitute for actually doing the calculation. But then at another level of detail, this workshop is about proteins, so here's a pathway from, for a folding of a knotted protein. It has a deep trefoil knot. It's an methyl RNA transferase protein, and I started it from two ends pulled apart, and the blue end, it's a ribbon representation, but we do have an atomistic set of coordinates. You see this end has looped, and at the moment if I pull the two ends nothing would happen, but this loop is going to unfold a bit and then cross over that red branch there. And now when it does that, the topology is subtly different. You can see that if I pull it now, something would happen, and now the red end is also going to make a loop and pass through And when it gets all the way through, the topology is sufficiently different that if I pull the ends, I've got a knot. So that's one of the most complicated pathways we've ever looked at. It took quite a while to even get an initial interpolation between the endpoints. If you just draw a straight line, you get complete nonsense. The chains just cross, so you have to do something else. But whichever of these three coarse graining levels or atomistic levels or accurate levels of computation we're using, I'm actually calculating observable properties from local minima and the pathways that connect them via stationary points. So I'll tell you a little bit about how we do that computation, because this is supposed to be pedagogical, and I'll give you some applications as well. But before I go any further, I need to introduce how we're going to think about these 3 n-dimensional landscapes, where n is the number of atoms. And I'll start with one of the key messages that was revealed itself early on when we started actually being able to look at this topology properly. So here we're going to use disconnectivity graphs, and I have 4 of them here, following Oren Becker and Martin Karplus. And these 4 graphs have a similar motif, even though they're completely different systems. So in a disconnectivity graph, in case you've never seen one before, the bottom of each line represents the energy of a local minimum. We join these minima together at the lowest energy where they can interconvert, and we know what that is because we've calculated the transition states. And we do that analysis at a discrete set of energy levels, which you can choose. So you want it to have enough of them to reveal the structure in the landscape, but not so many that it's totally confusing. The energy increases up the screen. The horizontal axis here is just chosen so that the lines don't overlap, but it can be an order parameter. And the 4 systems are a 55-atom atomic cluster with an icosahedral global minimum, an icosahedral shell representation, coarse-grained model of a virus capsid, a model of bulk silicon, which uses an empirical potential, Stillinger-Weber. It's a periodic boundary calculation. And then at the end, here's the GB1 peptide with a beta strand at the bottom. And the point about all these landscapes is they're unfrustrated. There's one motif, and there's no competition from anything low energy separated by a high barrier. So if you're in the wrong place, all you have to do to find the global minimum is go up a little bit and then down a long way. So these landscapes have a funneling aspect. They funnel trajectories to the global minimum over a wide range of temperature or total energy. So this is the structure that we expect for a good self-organizing system, a good structure seeker. And this is exceptional. These are the structures that we tend to notice because they often have high symmetry. High symmetry can be related to low energy or high energy, but it's not normal. It's selected for. So, for example, in a molecular beam, atomic clusters can be selected or by evolution in terms of peptides. And glassy systems are completely different. So at this point, somebody often asks me, what does a glassy landscape look like? And here is part of a glassy landscape calculated by Vanessa de Souza during her PhD, where we have a large number of competing amorphous structures separated by high barriers on a relevant thermal energy scale compared to the glass transition. And this structure is completely different from anything we see up here. It's the exact opposite. So this is what a glassy landscape looks like. And it's for a structural glass former. It's a binary mixture of Leonard-Jones particles. Right, so I'm going to use disconnectivity graphs all the way through this lecture. Are there any questions? Is that clear? The energy increases up the page. The bottom of every line is a local minimum. Everybody happy with that? Okay, then I will move on. Now, that paradigm for good structure-seeking systems is certainly true. It distracted us a bit for quite a long time, though, because actually we saw many systems that didn't really have a single funnel potential energy landscape. And then finally, when we came to do the Puma peptide, this is the p53 upregulated modulator of apoptosis protein, which is considered to be intrinsically disordered. So we were stimulated to do this system by Jane Clark, who studies it in the lab. And they had some experimental data where they saw bits of alpha helix. So we did this computationally. This was Yasmin Chibono. Here's a free energy landscape. It's projected, so let's not look at that one. Let's look at the free energy landscape for the disconnectivity graph. And here, it's somewhere in between. It's certainly not single-funneled. It's not glassy, really, either. It has a large number of competing low-energy structures with different bits of alpha helix in it. So what do we learn from that? Well, I think probably what happens is that there's an induced fit type mechanism for this promiscuous binder with different ligands. So when something comes in to bind to this, I think it will selectively stabilize one of these different motifs. And we're testing that hypothesis. And this led us to think that multifunctional landscapes are what you would need to encode a multifunctional system. And of course, nature has already beaten us to this, as usual. But I'm going to show you some other systems later on that might become design principles, for example, for biomolecular switches, where you would need a bistable landscape with two competing morphologies that you can switch between somehow via temperature or pH or an electric field or something. And these don't have to be biological. They could be a target from materials science. So the new paradigm, multifunctional landscapes for multifunctional systems. How do we know what's at the bottom of the landscape? If you don't know that, you don't know very much. And that's going to be one of the first demonstrations in the afternoon. So we're going to do basin hopping global optimization for structure prediction. And here we're following Lee and Shiraga. And we transform the surface into the basins of attraction of all the local minima. So the energy at a 3n dimensional position vector big X becomes the energy after doing a minimization. And this is my cartoon of the landscape. So we start with a surface, and this cross-section in red is the same cross-section in all four panels. So after doing the local minimization, we end up with a set of plateaus corresponding to the different energies of the possible local minima. The global minimum is over there. So it's a very non-local transformation. And if you look down on it from the top, every pixel has an energy. And this cross-section, if I now superimpose the original surface and the minima, you can see that we've gone off the edge of the scale here to find the global minimum. And this turns out to be extremely powerful. You just have to combine it with a way to walk between these different local minima, and you manage to beat most of the existing algorithms. And in fact, if you look on the OptBench website, you'll see that basin hopping has the best performance for most systems that we've looked at. Okay, so that's how we are going to find what's at the bottom of the landscape. And here's a gallery of a very small number of things that have been done with it. So atomic clusters, we're going to come back to this one, 38 atoms. The global minimum is a truncated octahedron. This is the unit cell for the crystal structure of that glassy landscape that I showed you a few minutes ago. So you can find papers in the literature that say this system has no crystal. And they're wrong, it does. And you can find it with basin hopping. Mark Miller found some really interesting knotted global minima with the Stockmayer potential, which is Leonard Jones plus a dipole moment. And here he made two representations of each of these global minima, where you have a blob for each particle or a chain. And the knots are predicted to be the global minima, where the dipole-dipole energy basically interferes with the isotropic particle-particle interaction. So if the dipole-dipole part dominates, you get chains and rings. If the isotropic part dominates, you get the same structures as for Leonard-Jones clusters, but somewhere in between, the prediction is knotted systems. And you can use this for polycyclic aromatic hydrocarbons, water, protonated water. The movie I showed you at the beginning was a representation of the Thomson problem with 1,602 particles on a sphere repelling each other. And you can use it for predicting protein structures as well. But you're not going to beat methods that use databases if there are enough structures in the database for your protein. but you will be able to do a good job that's useful for other systems where there isn't enough data. Okay, so I think I'll try and do a demo at this point. So we'll go to this screen, and this is not going to be a movie. This is going to be a demonstration on one core of this laptop, and we'll do an atomic cluster for 150 Lennard-Jones atoms seeded with today's date, and I'm just going to add it together, so it doesn't matter if it's the US or UK version. And on the left are snapshots of local minima that we're passing through, and on the right is the lowest one so far. And the colors mean something. So the blue atoms have the lowest pair energies, the red atoms have the highest pair energies, and the green ones are in between. And it managed to find the global minimum. So there are probably about 10 to the power 150 minima on this surface. But we've just found the global minimum in a few seconds. And I tried to slow it down by putting 3 atoms on the surface. So today was a good morning to find global minima. Let's see if it works in the afternoon. And I'll do another example later for a biomolecule. Okay, so 1 or 2 equations on this slide. I do need to do this one. There are a few later we could skip, but I need to explain how we get thermodynamics from the energy landscape at the most approximate level, and that uses the superposition approach. And here we simply write the global partition function as a sum over local minima, which is in principle exact. It's just a partitioning of the complete configuration space. And you can lump this over permutational isomers. So for each stationary point, or in fact for any configuration on the landscape, the number of different equivalent structures is governed by symmetry, and it's exact and analytical. And you can weight the sum by this term so you don't have to find them all. And this actually is important, particularly if you have a lot of interchangeable atoms of the same type. So for an atomic cluster with 100 atoms that are all the same, you have to allow for all those permutations. And in biological force fields, all atoms are not exchangeable because you have traditionally backbone atoms bound by harmonic springs and so on. So those carbon atoms are not exchangeable directly, but things like rotations of methyl groups and amide groups are. So you have to be careful about that. And the number of permutation inversion isomers for structure alpha is given by the product over all the factorials of over all the different atoms, carbon, oxygen, nitrogen, hydrogen, etc. in your system. The 2 is for an inversion symmetry, and O alpha is the order of the point group. So we write that as P over O alpha. And then the total partition function, this is the canonical one, but you can do it for microcanonical or anything else that you like, is written in terms of Z alpha. And we can actually do the sum in terms of the number of different structures instead, and take this part outside, so we only have to sample 1 stationary point of each sort. Now, for most biomolecules, O alpha is just 1. They don't have any point group symmetry. That's not always true. As we just discovered, for some cyclic peptides with identical residues, you can actually get pretty high symmetries for those, and then this becomes important. But I think it's probably already clear that it's important not to focus on biomolecules if you're thinking about methodology. The methods that I'm using are equally applicable to all these different aspects of molecular science with small adaptations. And so if you want to think about the most powerful way to do something, whether it's a rare event dynamics or enhanced thermodynamic sampling, you should be looking throughout the whole literature, not just at biomolecules. And so to be general, we need to keep this term. And an interesting result here is that high point group symmetry reduces the thermodynamic weight. So the order of the point group is on the bottom. So to show you a nice example of that, here's an 8-particle colloidal cluster. And this work was inspired by experiments at Harvard by Vinnie Mahanaran, where they do optical microscopy for polystyrene microspheres. And they found all the structures that we find using a simple model potential corresponding to a Morse potential with a very short range. And this is the potential energy disconnectivity graph. This is the free energy disconnectivity graph using the harmonic partition density of states for the vibrations at the experimental temperature. And so that means Z alpha is e to the potential energy over kT, and then you have to divide by the order of the point group, which is important here. And this term, beta is 1 over kT, nu bar is the geometric mean vibrational frequency. So it's the vibrational partition function for the cluster. 3n minus 6 is the number of vibrational degrees of freedom, and that's e to the minus free energy over kT. And amazingly, when you do that calculation with one adjustable parameter for the range, you actually get the observed experimental abundances for all these clusters within 1%. So it's startlingly accurate, even though for that calculation, even though these colloids actually have structure, really. And you notice that these branches look as though they're all at an energy of minus 18. Actually, they're not quite. They're slightly different. And that's because there are 18 nearest neighbor contacts in each of those structures. And this is a very short range potential, so it's actually almost counting the number of contacts. But this one has a pair of atoms that are actually slightly displaced from the perfect distance, but it manages to make almost an extra connection, 0.6 of an extra connection here. And this one stays the global minimum at the experimental temperature, but other things spread out all over the place, mostly due to the point group symmetry, but also the mean vibrational frequency. Okay, so that's a very powerful illustration of the superposition approach for thermodynamics. All we had to do was find the local minima and do a normal mode analysis, and we got the experimental occupation probabilities directly, accurately, but more than that, we can do the whole landscape, including the pathways as well. Okay, so that leads me on to more superposition type applications. So free energy basin hopping, in this case, instead of just focusing on the potential energy, we reject and accept structures according to a local free energy. So in normal basin hopping, you minimize, you find an energy, and then you perturb the structure any way you like, so long as it's ergodic, minimize again, and you accept or reject that structure based upon the change in potential energy or local free energy. So now we look at F nu minus F old, which has the difference of potential energy, and it has the order of the point groups and the vibrational partition functions in it. And here are two simple examples. This one's very boring, and this is the serine lysine dipeptide, which is one of our examples this afternoon. And here we're plotting the free energy against temperature relative to the global minimum. And in this case, the red line means it doesn't change. But for serine lysine, there are 3 different global minima at different temperatures. Starting at low temperature, it's this one, and then this curve crosses over, and that one becomes the global minimum, and at higher temperature, it's this one. And there are lots of other tricks that you can use to sample the space more efficiently. I'll mention one more in a minute. You don't have to use a Boltzmann type acceptance ratio here. We're not calculating thermodynamics directly. We're just trying to do structure prediction. So you can take any steps that you like, and you don't need detailed balance. Further examples of basin hopping, here's generalized basin hopping. Now in this case, we don't just optimize one thing, the energy. We can have biminima, which are minima in more than one space. So normally you would think about the configuration space, do a local minimization. Here we're doing that, but we're also defining a neighborhood for each local minimum. And this approach was derived by Dmitry Shebatov for nanoalloy clusters, where you have more than one sort of metal atom. So you have a chemical disorder problem to solve, as well as the structure with respect to the atoms in some close framework. And here you can define a neighborhood for each minimum by pair exchanges of atoms of different elements. So that's our local neighborhood, and you get a very efficient method if you scan that neighborhood and combine it with the local minimization in configuration space. So you define a BIminimum as a structure which cannot be improved by swapping different atoms and then minimizing. So it's a minimum in two different metric spaces, one of which is continuous and one of which is discrete. And here are some results. So this is for copper, silver, gold, 55 of different compositions as a function of composition. And we had some results to compare with from previous work. I think that's an evolutionary algorithm. This is a log scale. It's the mean first encounter time for the global minimum. So you have to generate statistics, find the global minimum 100 times or 1,000 times. And there are two different varieties of GBH, generalized basin hopping, one of which scans the whole neighborhood, and one of which uses a heuristic to guess which steps might work better. And you can see that both of them do rather well, this one in particular. And here is Dimitri's pseudocode for his top graphic, which I think is quite nice. Okay, so what does this have to do with biology? Well, it evolved into, appropriately enough, mutational basin hopping. This is another variety of generalized structure prediction, but now our discrete space becomes the sequence. So we do biminimization, and now we change the sequence, and it could be a protein or a nucleic acid, to optimize some property. And in this little example, which was done by Konstantin Roeder, he looked at these two nonopeptide hormones, oxytocin and vasopressin, and we used a very simple measure of binding energy. We're going to hear better ways to do that later. Here we just pulled it apart and relaxed it to have a guesstimate of the binding energy. And we looked at the binding to neurophysin 2, which is the carrier for vasopressin, but it can also bind oxytocin. And we started our simulations from the crystal structure with oxytocin, the wrong binding partner, and we wanted to optimize the binding energy, so we thought we should get vasopressin. The potential here is one flavor of amber with an implicit solvent. So the crystal structure, two views, side and top, are here. This is the hormone, and the key residues that we need to mutate are there. We also considered mutating residues of the carrier protein, neurophysin 2, to achieve higher binding energy, and that worked as well, actually. So when you run this calculation, you do blocks of ordinary basin hopping moves, and then you accept or reject mutations. So the greens are mutations that are accepted, the reds are proposed mutations that get rejected. And actually, to transform oxytocin to vasopressin, you need two overall mutations, I3F and L8R, and those are proposed and accepted fairly early on. This one is a wrong mutation. You don't want that, but it gets reversed later, and then you end up with the global minimum. So you see there are spikes in the energy, and these are the energies after minimization when you do the mutation. And the dots in the graph below are our guesstimate of the binding energy, which is part of the optimization procedure. So we have correct and incorrect mutations, and the incorrect ones get reversed. And we also mutated some of the key interaction sites, which improve the binding to oxytocin. So you can target things differently. Okay. Then it's quite easy to make far more difficult optimization problems. You just need to make the system bigger sometimes. Some big systems are easy, but some can become very difficult. So I'll show you another example for a fragment of the Alzheimer's protein later. This is A-beta 1 to 42, and it was work done by Birgit Strödel, where we looked at a charm-19 representation for multiple oligomers of A-beta, starting with the monomer. And we wanted to use charm-19 because there's an a very useful implicit solvent model and an implicit membrane model, IMM1, so it's cheap to simulate. And here the two black lines in the figure represent the extent of the membrane. So for the monomer, there's a transmembrane part with beta turns in it and an outside the membrane part. Actually, the monomer prefers to sit on the surface. That's the prediction anyway. But once you get to higher oligomers, like the dimer, where you have these beta sheets organized together, those become competitive and become the global minimum. And for larger structures, you start making quite interesting motifs. Now, these are quite large, so if you run plain basin hopping, it will take a long time to find them. Birgit ran basin hopping parallel tempering scheme, where you have parallel basin hopping runs at different temperatures that can exchange with each other. So this is a way to make basin hopping parallelizable, and I will show you the structure of that. So this is the predicted global minimum for an octamer, where she has colored the 8 components differently. All the side chains are in there just to show you that we did them. And if I take them out, I think you will be able to see that there's actually a gap down the middle. And the membrane, the part in the membrane has the little turns at the end. But the predicted gap in the middle would be large enough to leak. So if this gets stuck in a membrane, it would destroy homeostasis. Ions could leak through this. So that would be a mechanism for cell death. And now I'm going to do something really simple, just a little polyalanine, and this will illustrate 2 things, one being the superposition approach to thermodynamics, and the other one being we're all at the mercy of the empirical potentials involved. So I set this as a benchmarking question for Sandeep Samani when he arrived to do a postdoc. The problem with the biological systems is lack of benchmarks, in my opinion. So all the really good benchmarks where we can agree on what the answer is tend to be for simple potentials and atomic clusters. And when we go to more complicated biosystems, even if you think you're doing the same potential, you may actually have a different cutoff or a different solvent model or something. So I thought, well, we should try and find some benchmarks for where everybody will agree on the right answer. So let's compare just simple polyalanines. We'll do it in vacuum, so no one can argue about the solvent model. And we'll try charm and amber and see what we get. So Sandeep ran parallel tempering, molecular dynamics replica exchange, and of course the superposition calculation from the landscape. And he made disconductivity graphs for this system. Here's the heat capacity as a function of temperature predicted from MD-Rex. The superposition curve is not bad. It has a low temperature peak in the right place. The peak height isn't quite right. And this is a melting type peak, and it's shifted to the right, and that's because high energy minima tend to have softer vibrational frequencies, but we don't model that because they're anharmonic, so it's slightly in the wrong place. The melting peak is shifted to higher temperature because we've disfavored the high energy minima. This peak at low temperature is caused by a switch between the minima in the red branches here and the black ones, and that's just an end group moving around, but the barrier is quite large and they have different vibrational frequencies, so they're different enough to give a low temperature peak here, which is a bit like a first order phase transition. And so why would you bother doing the superposition calculation? Well, because it's many orders of magnitude quicker than any of these other things, and it automatically satisfies ergodicity, and it's very insightful. Whoops. So we'll go back. Right, so here is the converged MD-Rex curve, and this is the heat capacity calculated from superposition, and I'm going to add the minima together, starting from the lowest one. So at the moment, that's the curve we get, and we're up to 4 minima, and it's wrong so far, but let's see what happens when I run the movie. When I get up to about 100 minima, we've got most of that peak. So I can tell you exactly which minima are contributing to features of the heat capacity here. And then as we go on further, to get the melting type peak, we've gone to thousands of minima. And this illustrates the difference between landscape entropy in terms of the number of minima and the entropy per local minimum that corresponds to the local well. So there are 2 sources of entropy. One comes from each minimum itself, and the other, the convolution, comes from superimposing all those minima on the landscape. And this melting type transition is driven by the number of minima at high energy. So it's more like a melting transition. So the superposition approach is very insightful, it's very fast, and it was correct on day one, whereas it actually took us a surprisingly long time to converge the MD-Rex and parallel tempering results because of all the niceties with how often should you make the exchange attempts, what should the schedule of temperatures be, and so on. And we found that you could actually get what appeared to be converged curves that were completely wrong if you didn't run it for long enough, and if you'd made bad choices about the spacing of the temperatures, for example. Okay, so it's a very simple peptide. We'd hope to get the same answer for any potential, wouldn't we? If we can't get this right, then we have a problem doing something bigger. Well, here's amber, here's MD-Rex, here's the superposition calculation. It's not very different, so it doesn't look too bad. Here's the landscape. But in a way, this is entirely wrong. So, in fact, Sandeep ran this calculation, and normally we don't allow for chirality inversions when we take our steps in basin hopping. And he accidentally turned that off, and he allowed those steps. And he discovered that actually the global minimum for amber is not all L, it's a mixture of L and D amino acids. Now look at the landscape here when we allow all these exchanges, and look at the scale, 5 kcals per mole. These are gigantic barriers between different sets of minima that all have the same LD pattern. So I'll move back again. This is one of those subfunnels for a particular all L pattern. I think we might need another pointer before I finish. It's getting a bit faint. So this is a subfunnel. Look at the scale, 1 kcal per mole. And here we have a set of different funnels with different LD isomers. So to get that right, to converge the global thermodynamics here with MD-Rex, you would need thousands of replicas, and the highest temperature would be temperature at the core of the sun. Superposition gets it right rather quickly. Okay, yeah. Let's just see how this one is doing. That's probably a bit brighter, so I'll save that as backup. And you need to be careful what question you actually ask here. So experimentally, if you start a normal experiment, you'll only see one of these subfunnels. You'll never get out of it. So maybe you do just want to stay in one of them. So be careful what you sample. You want to compare with a particular experiment. But these barriers are 90 kcals per mole, so you're not going to go over those in anything thermal. And you're also not going to find the global minimum with any method that's really looking for thermodynamics. So how easy is it to find the global minimum when we have barriers of 90 kcal per mole? Let's have a look. So I'm going to run conventional basin hopping on one core of the laptop for the tetraalanine with amber. So it's amber 99SB. And I seed it with the date. And on the left, our local minima that we're passing through. We're starting with all L. This is already a mixture of LD. Oh, and that's the global minimum already. Okay, good day to look for that. So it's a mixture of LD isomers which can make an extra hydrogen bond. That's really why it likes this structure. But this is completely different from the result with charm, by the way. So things are different even for 4 alanines. And finding the global minimum here, if you really wanted to allow LD exchange, you need to do basin hopping. Basin hopping will find it very quickly. It takes unphysical steps through the landscape, but then it fixes that by minimizing. That's basically how it works. Okay, so that's nearly 40 minutes. Any questions so far? If not, I'll just keep going and have a drink. So I'm going to, yeah. Anything? We can do questions at the end as well. So, yes, please. Yes, go on.
how can we judge if our calculation reached the convergence, or if we are sampling all the basin of the system?
Yeah. So, okay. If it's a small system, you just stop finding new structures, and pragmatically, you run it for twice as long and see if anything changes. If it's a large system, it's become a sampling problem, and you need to do something different. You can't enumerate all the minima. There wouldn't be enough atoms in the universe to make enough hard disks to store all the coordinates. So for that sort of problem, we need to use Basin sampling. And again, this is not deterministic, it's stochastic. So if you want to guess whether it's converged or not, you really can't do much better than run it for longer. You can make measures using Bayesian type analysis to see whether you think the probability that you finished is higher or not. But there isn't really much substitute for running it for longer. And of course, agreement with experiment is the gold standard for knowing whether you've got it right for a specific system. And then you'd like to make predictions for things where you don't have experiments. And so you hope that your parameters are transferable from one system to another in that case. And so when we come to designing some switches later on, that's the sort of approach we would need. We make a prediction, and then we find experimentalists who are, by and large, fantastic, and they always seem to impress me. I reckon they can make anything, they just need enough motivation. So if we make predictions, I think that they will try and build it, especially if it could be exciting. Okay, but this is stochastic, it's not deterministic. Right. So that was my demonstration, which I've done. And just a couple of slides on Basin sampling. So this is actually your question. What are we going to do for something bigger? We can't enumerate everything there, and that would be a dumb tactic. So instead, we use Basin sampling to get global thermodynamics. And the idea again here is to solve the broken ergodicity problem. And we solve broken ergodicity using global optimization. So we run basin hopping to find what's at the bottom of the landscape. And then you use your favorite high temperature technique to do the high temperature part. So parallel tempering or MD-Rex or something. Nested sampling works as well. And now you've got to stick them together. So you interpolate between them. And the way I'm going to do that is to use a two-dimensional density of states. So we've now got an approximation. We're going to try to do this quantitatively, so we want anharmonicity this time. And I'm going to use a form for the interpolation that's suggested by an anharmonic potential, the Morse potential, which of course can dissociate, and is solvable analytically. So there's an analytical density of states for the Morse potential. It's quite complicated, but it basically has a series in the energy difference. So what we do is run the high temperature part, and we quench periodically, and we look at where we quench to. That's energy bin Q, from an instantaneous potential energy bin I, and a replica R which has a temperature, and that's the number of quenches that go to that particular point. It gives us a two-dimensional histogram, and the canonical probability distribution is then P of V instantaneous, V quench, and the temperature. And it's proportional to the omega C, which is a configurational density of states, which I associate with the two bins for the quench energy and the potential energy, and there's a Boltzmann factor. And this is actually the form that we fit to. Here is the number of vibrational degrees of freedom divided by 2. Here's an anharmonic fitting term. The two fitting parameters are AQ and BQ. This is a prefactor. At low temperature, this is analytical. Comes from the harmonic approximation, and it has the energy difference between the instantaneous potential energy and the quench energy, and this gives us part of a power series in that delta V. So that's all I'm going to tell you about it, but I'll show you some results. And again, our benchmarks are atomic clusters here, where we can all agree on the potential. It's just Leonard Jones, and we hope everybody can code that, and we should be able to agree on the answer. So there are alternative calculations by people like Florent Calvo and Vladimir Mandelstam, and we agree on the answer. And in this case, I managed to get an accurate heat capacity curve, and it took about 22 minutes on 24 cores, compared to 110 hours for parallel tempering. And this is an interesting benchmark system because it has a low temperature heat capacity peak. It has two competing morphologies separated by a high barrier. So this gives us a solid-solid type phase transition at low temperature where the barrier is 30 kT. So it's a broken ergodicity problem. And then there's a melting peak up here, which is driven by the landscape entropy, the number of minima, as well as the local entropy within each well. This is a magnification of the low temperature solid-solid peak. This is the harmonic superposition approach, and you see it's quantitative at low temperature. There's very little anharmonicity in the wells. There's still some anharmonicity from having different local minima. And so the reference is a converged parallel tempering calculation. So you can do this by brute force with parallel tempering, and the BSP T-curve is the red one. And in fact, I just wanted to show you that you can assign the heat capacity features using the superposition type analysis where you write the global partition function as a sum. So here's a disconnectivity graph for this landscape. Here I'm showing more minima, which are relevant at a higher temperature. This is the temperature 0.0268 of the solid-solid heat capacity peak. And this is the temperature for the melting peak. And you can now ask the question, which minima do you need to get those peaks right? And for the low temperature peak, you only need 4 of them. And the red one is the global potential energy minimum, which we're coming from as we raise the temperature. And there are 3 blue lines here, I hope you can see them, where those are the minima that are going to be occupied on the other side of that transition. Now you can actually write the heat capacity within the harmonic superposition approximation in terms of the occupation probability gradients, dP by dt. So P gamma is the probability that you're in minimum gamma at temperature T. And we look at the gradient of that with respect to temperature, and we can write the total CV as a sum over the parts with a positive and a negative occupation probability gradient. So these are the minima we're coming from. These are the minima we're going to. Of course, all of these are non-zero, but how many of them do you need to get 99% of that heat capacity peak? So you can stop doing this sum. You start from the bottom up when you've basically converged the feature that you care about. And in this case, for the low temperature peak, you only need these 4 minima. But at the melting point, we actually need nearly all the minima to get 99% of that large melting heat capacity peak. And now we have lots of red minima, which were occupied and now have a negative occupation probability gradient, and their probability is being translated into the minima in blue. So most of the landscape is involved in that transition, as you would expect, because it's driven by the landscape entropy. Is that clear enough? So coming soon, biological applications. Right, so a change of tack. So I've done structure prediction and a bit of thermodynamics. So now I'd like to tell you about pathways and rates. So most of what we've done so far has been based upon local minima. But we can calculate the pathways that connect them. That's how we get the disconnectivity graphs. And if I want to tell you about global dynamics and rare events, I'm going to do discrete path sampling, and I'm going to formulate the rates in terms of pathways on the landscape. So here are 2 cartoons of a potential energy landscape with reactants B and products A, and they're made up of lots of little local minima, little b and little a. And in general, we would need reactants, products, and stuff in between, so I for intervening minima. And you only get single exponential kinetics in this case if we can put these intervening minima in steady state, so the time rate of change of their occupation probabilities, so I'm using pi again here for the occupation probability of minimum I. Those have to be 0, and we also need local equilibrium within the products and reactants. And then you get single exponential kinetics. And furthermore, we can actually work out, for that steady state SS approximation, the phenomenological rate constant from B to A in terms of an infinite sum over all the pathways. So these P's are branching probabilities. So Pi1, I2 is the probability that if you're in I2, the next minimum is I1. This is a sum over all the infinite number of pathways. I've sketched a few in the cartoon. But it's weighted by the conditional probability that you start in minimum little b, so p little b equilibrium over p big B, and there's a waiting time for escape from that minimum, a reciprocal, because this is a rate. And then after you scratch your head for a few years, you realize that this infinite sum is no more than Onsaga's committer probability, CBA, the probability that you go to products from little b without going back to reactants. So it's a neat way to write it. And we're going to have to try and work out how we converge our landscape to get converged rate constants for the process that we're interested in. And in brief, discrete path sampling builds these connected databases of stationary points, local minima connected by transition states, and I have a few slides on how we actually do that, some of which we might skip if you want more applications. And you can analyze that database once you've got it in all sorts of ways. There's a huge literature on network flows, some of which is based on electrical circuits, some of which is more modern, but rediscovery partly, because the literature is so diverse, you can hardly help that. You can pick out the largest contributions to that rate constant using Dijkstra's algorithm or recursive enumeration. And here your edge weights are minus the log of the branching probability. And there's a hierarchy of rate constants. So the simplest one is the one I just showed you with the steady state approximation for the intervening minima. And this has the committer probability times the conditional occupation probability and an escape time. You can take out the steady state approximation. And in that case, all that changes is this waiting time becomes the waiting time for escape to any A or B minimum. And if you want the exact rate, which you get from the exact mean first passage time, it just becomes the conditional occupation probability divided by the mean first passage time from little b to any A minimum, allowing for return to the reactant region. So there's a hierarchy of rate constants, and these waiting times obey this set of conditions. So the escape time from one minimum is, of course, the fastest, and the escape to a product minimum is the longest. And under different conditions, these can be the same, but in general, they're not. So this is formally exact within a Markov assumption for all those transitions, which can be enormous. So our longest pathway at the moment is 3,600 transition states, and that's for hemagglutinin, a virus capsid surface protein, and it's for the fusion peptide changing position. So these can be extremely long pathways where you need this sum. That one would be very inaccurate. Of course, we are also at the mercy of incomplete sampling. That was your question. How do you know if you've converged? And usually we just use harmonic densities of states to estimate the rate constants, and you can choose your favorite unimolecular rate theory. So we normally use transition state theory, but it could be anything you like, and it could even be actual dynamics if you have a big enough computer budget. So you could do that for your pathway. So that is, in essence, what we're doing to find and grow the database. I haven't told you how we find the stationary points yet, but I will do in a minute. The benchmarks and the methods, again, this is just a summary, but for minimizing's easy. We just use LBFGS. This is a custom version where I took out the line searches, which we think is the fastest. So that's easy. But transition states, we've spent nearly all our time finding transition states. So to find a transition state, and I won't walk outside the tape, but to find a transition state is different. You have to be balanced on a knife edge. So we've got one direction where forwards and backwards is downhill, and all the perpendicular directions are uphill. So you're balanced here in between. And to know that you're on the knife edge, you need second derivative information. You need a curvature. You need to know that you're at a peak. So that makes the calculations more involved. And we use hybrid eigenvector following to do that. If you give me one structure, and if you want to work out where to start those calculations from, we use double-ended searches using a doubly nudged elastic band approach. And the three programs that we're going to look at this afternoon are GMIN for structure prediction, Optim does the transition states and pathways, and PathSample is a driver for Optim, which enables you to fill your chosen cluster with as many Optim jobs as your computer officers will allow you before they realize that you're about to crash the system and fill the disk. So PathSample spawns Optim jobs which don't need to talk to each other, so they're embarrassingly parallel, and it collects the results and decides what you should try to connect next. Optim has interfaces to dozens of electronic structure codes, Games US, Games UK, NWChem, CPMD, MolPro, OneTep, CastStep, Gaussian, CADPAC, NWChem, Quantum Espresso, VASP, and possibly some I've forgotten about, and Amber, Charm, GROMAX, and now it has a ReaxFF force field as well. You can get the current SVN tarball image from our website, so that's updated at 9 o'clock every morning, so you can get all our latest bugs. There's full documentation. There are benchmarks, so there are transition state benchmarks here. The OptBench test suite is hosted by Graham Henkelman in Texas, so he's another NEB expert more in materials science, but he does phase transitions there as well. And there are curated examples at the GitHub, some of which you're going to see with John Morgan's help. And I could tell you a little bit about this, but would you prefer to see details of transition state searches or some applications for coarse graining? Who would like to see coarse-grained applications? Who would like more equations? I'm afraid you lost, but I'll summarize them. Okay, so this is the bit I could skip through fairly quickly because it's really quite well established what the most efficient methods are. You need to use doubly nudged elastic bands, which come from the old chain of states methods that Ron Elber and people like Pratt used originally. They evolved into nudged elastic band from Hannes Jonsson and Graham Henkelman in particular, and you just have images of the system connected by elastic bands, and technical issues mean that you have to be a bit careful about the gradients, because if you're not, the images will slide down or do corner cutting. But that's not very exciting, and it is basically summarized by the gradient that you really want to use. And we are doing this elastic band type calculation to propose candidates for single-ended transition state searches, which I will tell you a bit more about because they're a bit more interesting. So once you have high points along this chain of states, we take each one of those and we do a single-ended search using hybrid eigenvector following, and that is designed to find a single transition state, and then you must find the minima that connect it. So I'll tell you a bit more about hybrid eigenvector following. This is a bit less dirty. Because you actually know what the functional is that you're trying to minimize. So here we use a variational approach. We want to avoid calculating all the second derivatives if we can. And you can avoid that, and you can avoid diagonalizing that Hessian second derivative matrix. But we do want to walk uphill along a Hessian eigenvector that corresponds to a soft degree of freedom. So we do need at least one eigenvalue and eigenvector. But we want to do that without calculating the second derivatives or diagonalizing that matrix. And we do it by defining that eigenvalue, lambda, for a displacement, for a position x, a displacement x, in terms of an expectation value of the second derivative matrix divided by normalization. And you can formulate lambda of x, which Art Voter did in 1997, and it's the same as what Graham Henkelman and Hannes Jonsson do in the Dimer method. You can formulate it as a two-sided derivative that just involves the potential. This is a two-sided value. You can differentiate that with respect to the step. And what you want to do is minimize this to find the smallest eigenvalue, the softest mode. Actually, you don't want to do that because there are zero eigenvalues, which are overall translation and rotation. So you've got to get rid of those, or you'll find them by mistake. That's easy. You can project them out because they're analytical. So that's not a problem, and you can shift them if you like instead. You use the analytical forms. So this is how we normally calculate this Rayleigh-Ritz ratio and its derivative for walking uphill. Now, actually, if you're going to do proteins, there is another problem. Once you've got this direction, you can take a step uphill and minimize in the tangent space. Not too much, or you'll fall off and go back down again. So you have to iterate this procedure. But for systems where the magnitude of the energy is very large, you can actually get into trouble with precision. And this didn't happen for quite a long time until our computers got large enough to do bigger proteins, where the absolute value of the energy gets larger and larger, and the fractional bit that you need gets smaller and smaller. And then we actually had problems with this two-sided method. But actually, you can solve that by using a different representation of lambda of x. You can do a Taylor series expansion, and instead of using the energy v of x, you use the gradient grad v, and a two-sided gradient with a dot product. Now, the truncation error is twice as large here as it was for the original two-sided representation. But in terms of precision, if epsilon's the fractional error in terms of floating point representation of a real number, the round-off error for this is a lot smaller. It's much more precise. And so we automatically switch to this representation when when the energy becomes large in magnitude. And that works perfectly well, so you can do 10,000 atoms with this. Any questions? Well, I'll show you a couple more landscapes now then, before I go on to a few more bio examples. So if you're good at finding transition states, then you get very excited when somebody like Stuart Althorpe, who does quantum dynamics, tells you about the instanton approach. So Stuart and Jeremy Richardson and other people have been pioneering this method for a representation of quantum dynamics, and it comes from Feynman's representation of the partition function, where you split this partition function up using a factorization into imaginary time slices. And this leads you to Feynman's expression for the partition function q beta in terms of an effective potential. So here P is the number of beads in an imaginary time representation. And UP is a sum over the potential energies at these 3 n-dimensional configurations with harmonic springs between them and cyclic boundary conditions. And this force constant depends upon the temperature and the number of slices. And then my ears pricked up when Stuart explained that this is, a classical potential for a ring polymer, and the transition states of this potential give you a finite difference approximation to these instanton pathways. And this gives you tunneling, splittings, and rates. And we can find transition states for systems with 10,000 degrees of freedom. So if they need 300 images here to get an accurate quantum partition function, we can do that. And it means that we could move on from smaller water clusters to bigger ones. And I'd just like to show you what we've been doing with that. So here is a rearrangement of the water trimer. It's a different one from the one I showed earlier. It's bifurcation tunneling, where one of the water molecules is a double hydrogen bond donor and one is a double hydrogen bond acceptor. And this produces smaller tunneling splittings than the flip, because we're actually making and breaking bonds. But Richard Sakeley's brilliant experiments in Berkeley using cavity ring down have a megahertz resolution, so they can resolve this tunneling splitting. And it's a rearrangement between permutational isomers of the same water trimer. So these are in resonance. Each one of these local minima supports an identical stack of row vibrational wave functions. And if they can leak through the barrier that separates them sufficiently, they interfere and give you the tunneling splittings, and they do here. So what we did was look for transition states and minima as well of that potential with P time slices, P beads. So this looks like the same system. It is, but I've now got 25 copies of it. And we're at a local minimum where all the images have collapsed to one structure. But look what happens on the pathway. That's the transition state and it's the instanton. And the hydrogens have delocalized. So this delocalization tells you how quantum those atoms are. So this one is a little bit quantum, but it goes back to where it was. These two were involved in that bifurcation tunneling motion. So you'd expect them to be pretty quantum. And via some clever mathematics that Stuart and Jeremy and other people have pioneered, you can calculate rates and tunneling splittings from this. More than that, you can make a whole new landscape. So I'm going to show you two new forms of landscape. One is for that path integral representation, and here I'm showing you the landscape for water dimer. And remember, it was a function of temperature. So how quantum versus classical it appears depends upon beta, 1 over kT. So low temperature is more quantum. And in this water dimer system, this is a magnification of that panel there. We have 8 different permutational isomers of the local minima, which can interconvert when we go through these 2 transition states. And there are actually 2 more transition states, which lead to shifts of the spectrum. And we found when we looked at the whole landscape with an MB pole potential, which is really very good for a very large number of beads, that we also got some delocalized local minima here. Now, look at how the landscape changes with temperature. What happens is that these beads spread out over the pathway. So at high temperature, they collapse to the classical result, and all the beads are on the transition state, or they're at the local minima. But for transition state at finite temperature, the beads spread out, and the lower the temperature, the further they spread. And the further they spread along the pathway, the lower the energy will be, because they get closer to the local minima. So that's why, as the temperature falls, these barriers decrease. And it enables me to show you this pathway. So here we've got 200 beads, which is why they look as though they're on top of each other everywhere. And it's an exchange process where the silver and the blue protons are going to change their roles, but they're all involved. They've all delocalized. The oxygens are in green. And the new permutational isomer is this one, where the blue proton is shared. And as we bounce backwards, the silver proton is shared at the other end. So these are permutation inversion isomers that support an identical stack of row-vibronic wave functions. And this gives a big tunneling splitting. Okay, the other new sort of landscape is for machine learning. So this is a bioinformatics meets biology workshop. So I thought I'd put in one machine learning slide. Now, here we're thinking about neural networks like this one. So this is a neural network with 3 inputs and 4 outputs in blue and red. The inputs are X, the outputs are Y, with one hidden layer in this case in green, and edge weights between them. And the neural network has multiple minima. If it has multiple minima, we've got a landscape. And so we can search the landscape. We can find transition states. I don't know what they mean, but we hope to find out and use this to see if we can actually make better predictions with the results. So in this case, my test example is a geometry optimization for a triatomic cluster. And I've chosen a potential that has 4 local minima. There are 3 different isomers of the linear minimum with the red, blue, and green atoms in the middle. And there's a triangular, equilateral triangle local minimum, which is competitive with them. And my test here is to try and guess which of these 4 local minima will be found from a given starting point. And the starting point is some position in the configuration space, which is 3-dimensional. You can have 3 bond lengths here, for example. That gives you a unique representation of any geometry. Now, there are pixels in this plot on the right, and I've colored each pixel, which corresponds to a different starting geometry, according to which of the 4 local minima you fall into. So the red pixels go to that one, the blue to this one, the green to that one, and the gray ones go to the equilateral triangle. Now, on the left is a disconnectivity graph for the neural network fits the predictions from training data. And I've done the same trick here. I've used the same projection through the configuration space, but this time I've colored the pixels according to the predicted probabilities of finding the 4 minima from my neural network solution. And you can see these 2 low-lying minima, that one's the global minimum, are very similar to the right answer. They're not quite the same. You see that gray bit isn't exactly right here, but they're very, very close. As you go up the landscape, the fits are disastrous. These are terrible. So on one screen, I'm doing molecular geometry optimization. On another panel, I'm trying to do prediction of patient death in hospital or sepsis onset or whether people should be discharged from the emergency room. And so if I'm trying to make predictions for clinical diagnostic support, I want this minimum, not that one, or I'm going to guess wrong, and we're going to discharge the patient too early, and they're going to die. But we better benchmark it on something that's a bit less important, like this. So I can generate infinite amounts of data for this system and test and benchmark things cleanly. So that's our new sort of landscape for machine learning. Any questions about that one? We'll do a bit more biology in that case in a minute. But we do need to extract rates from our network, so I will tell you a little bit about that. And that's an hour and 8. Okay, that's fine. So now, to actually extract the rates from our landscape, we use graph transformation. This is a deterministic procedure, and it renormalizes the branching probabilities, p gamma beta, the chance of going from beta to gamma if you start in beta, and it renormalizes the waiting times. And it does this in a very precise way, which means that we can do it almost independent of temperature. And this table has the timings for calculating or converging the phenomenological rate constants for, actually it's a beta 3S protein, using parts of the database at different temperatures where we've lumped some of the minima together to reduce the number of minima and transition states, N-min and NTS, because successive over-relaxation and kinetic Monte Carlo were really struggling for some of these problems. The blanks here mean that I could not converge kinetic Monte Carlo runs in the time available between power cuts in Cambridge. So you can see this one took 1 million seconds, whereas this graph transformation procedure took 35 and is basically temperature independent. Successive over-relaxation is all right if the temperature is high enough or if there are few enough minima, but it scales disastrously. So this is accurate, precise, and much, much faster than these other stochastic methods. This one really is deterministic. So when I show you a rate constant, that's how I got it. And here's an example of broken ergodicity for an atomic cluster with 38 atoms. It's one of our favorite benchmark systems, which used to be a benchmark for global optimization, but it's now too easy. Remember, I showed you 150 atoms earlier. The global minimum that John Doyfe found in 1997 is actually a truncated octahedron. I showed you it on that slide before. But if you just relax the system at a reasonable rate, you normally end up here in a fragment of icosahedron because it has higher entropy. And the heat capacity shows this solid-solid transition feature here at low temperature. And at the equilibrium, that barrier is about 30 kT, and there's a melting peak here. And here's the occupation probability for FCC and icosahedral parts of the system. And this is all in reduced units for the Lennard-Jones potential. And here I'm starting from a high energy, a high temperature distribution, and I'm monitoring how quickly we relax into the icosahedron and the FCC global minimum. And if you go on for about 10 to the 9 steps, it looks as though you've almost finished. We have plateaus here, but you haven't actually. You end up in equilibrium on a longer time scale around 10 to the 13 units. Right, it's a double funnel landscape. Double funnel landscapes are often associated with a low temperature heat capacity peak here and a separation of relaxation timescales. And that was true for that alanine peptide I showed you earlier as well. The two timescales are, there's some chance of relaxing to the right answer here straight away, but you're more likely to end up in the wrong place. And then you've got to climb out again. That's our second timescale. So the two timescales are that one here and this one. And that's nice and clean, but if you make more and more funnels, you get more and more timescales and more overlapping heat capacity peaks, and you end up with a glassy system. Now, we did this one in 1999 and 1998, actually, and I was quite excited. We've been waiting since then for somebody else to do it. So there was a big attempt that used a large amount of supercomputer time, and actually they used 10 to the 5 hours of supercomputer time, but they didn't actually find the right pathway. But this paper did, and they only needed 100 hours, and they actually have the correct rates as well, though they haven't published them yet. So they managed to get this right in 100 hours. And so I'm going to have a go, because I have or at least 15 minutes left. So I'm going to run this, and this is a demo that's going to run on 4 cores of this laptop, so it's not a movie, and all hell is about to break loose. So we've got a random seed, and we're going to try and make an initial connection between the 2 branches of that system, and it's got 6 steps today, and I'm going to show you, oh good, it worked. That was the whole point of using 1024-768. It's all sized for that. So the initial pathway in black, the new best pathway in blue, and these are the rate constants. We're starting from blue, and we would like to converge the forward and backward rates to red. This is an Arrhenius plot. Log of the rate constant against 1 over t. You can see it just jumped by 20 orders of magnitude. So we found a better pathway, and it's got lower barriers on it, and it's getting still better. It's not quite converged yet. And the pathway is getting longer, but the barrier is getting shorter. So it's probably near enough, actually. You can see, if you've got good eyes, that there's still a discrepancy at higher temperature. This is 1 over t. And at higher temperature, you need to converge more pathways. But at low temperature, nearly all the probability is going through a few pathways, a few bottlenecks, which we've converged fairly quickly. So we didn't need 100 hours. We needed less than a minute. And if I show you the pathway, this is a fragment of FCC lattice. It's got octahedral symmetry, and the other end is this one, which has C5V symmetry. It's a fragment of an icosahedron. So if I go back to the beginning and run this, the pathway had of order 10 transition states on it. The coloring is the same as before, so the blue atoms are the most tightly bound, the red are the most weakly bound, the green are in between, and that changes as you go along the pathway. There are localized rearrangements, delocalized rearrangements. There isn't an order parameter. There isn't a reaction coordinate you could have guessed. And that's a nice clean benchmark because everybody should be able to program the Lennard-Jones potential. So a few bioexamples. This is one done by Konstantin Roeder. So it's a coiled-coiled peptide. And we were interested in this because experimentally, it's tetrameric, but this mutation E20S disrupts a key salt bridge. So the native state is the landscape on the left, the mutant is on the right, and we've got parallel and anti-parallel dimers here. The mutation destabilizes the parallel one, and we have a lower barrier for interconversion here, where we can have twisted parts for the intervening minima. So here, those don't exist, and the barriers are higher. And so if you want to design a biomolecular switch, you need to be able to go between 2 different morphologies. So these would be significantly different. They'd have different dipole moments and physical properties. And you need to be able to do it as a function of something like temperature. And I'll show you the pathway. Oh, this is the pathway for rearrangement of 2 machine learning minima. So you're actually one of the first audiences to see this. And it looks like a 2-dimensional lava lamp. I like that, but we'll move on to the coil-coil, if it will let me. Yeah. So these are 2 views of the coil-coil transformation pathway, which are going to show us different features. It's going to curve around and kink around one of the helices. So they're in step. It's the same movie from different orientations. So we're looking down one of them. The other is basically kinking around it. And there you go. So it will pause there and then go backwards. And notice that this part has spread out. And there are a lot of transition states in this pathway. But it wasn't a difficult sampling problem. This was reasonably straightforward. So that would be a nano device, potentially. We've looked at aggregation of fragments of A beta. So this is the landscape for A beta 17 to 42, the monomer. And you can see it has lots of different local funnels with bits of secondary structure, and it looks pretty disordered. And I'm going to call that a multi-funnel landscape. And Konstantin Roeder again did this work where he looked at making the pentamer from the tetramer and seeing how the landscape could become frustrated when misaligned monomers add on to the best tetrameric beta stack. And the barriers between these different morphologies are actually very large. So this explains why you get structural heterogeneity, because you have lots of kinetic traps here. And it looks like if you want to aggregate efficiently, you would need secondary nucleation or something else. And of course, we're very glad if it's not efficient, because the more efficient it is, the faster we get Alzheimer's disease. So it's good that this one takes years. And remember that we're using geometry optimization to sample all these pathways and barriers and rates. And actually, it's no slower to find a high barrier than a low one. And the rate theory that we're using is more accurate for high barriers. So the slower the process is, the better we like it. And so this, we can do weeks, days, years with this sort of approach. And that's the sort of timescale that might actually be applicable here. So a DNA example, and this was work done by Tristan Cragnolini, and he used the higher potential, so it's a coarse-grained model for the nucleic acid, and it's for a G quadruplex. So G quadruplexes contain quartets of guanine, and they decrease the activity of telomerase that maintains the length of repeats. So these are incredibly important as potential drug targets, because when they misfunction, you're quite potentially going to get cancer from them. And I'm showing you the potential energy landscape and a free energy landscape on the right. And the left, we've got a crystal structure here, and these other structures are NMR. And the NMR structures belong to separate funnels, but they actually are they're not at the bottom of them. There's some distance up from the bottom. But when you calculate the free energy landscape, those NMR structures all move to the bottom of their respective funnels. So this made Tristan very happy, because it suggested that the potential they were using is good, even though it's coarse-grained and fitted elsewhere. The barriers between these things are very large again. So the timescales involved are long for interconversion, which is what you would expect, because it's a very complicated process. And I may need to go backwards and forwards here. Okay, so here's a cartoon representation, and this is a very complicated pathway. I'm going to speed it up, because otherwise we'll be here for too long. We need to, and in fact I'll skip forward, we need to make quartets of the guanine bases that stack into 3 layers. And this is just the fastest path extracted from the database. When I give you rates, I'm summing the infinite sum of all the possible pathways on the landscape. Here we've just extracted what pretends to be the quickest one. And it's a bit like a nightmare Rubik cube, where you have to get some of these things in the right order. And eventually you can see that the 4 guanines in 3 stacks are going to come together. And if I skip to the end, it's supposed to end up there, and it takes a long time. But it's coarse-grained potential, so we can do that one. Okay, and so I will finish in a few minutes. I would like to show you a couple of coarse-grained models, and I'll stop. So we use exactly the same methodology to do coarse-grained modeling, with a few tricks like local rigid bodies and local rigidification. And here's just a gallery of things that we've looked at, like models of virus capsids using decorated pyramids, ellipsoids, and this was work done by Szilard Fejzsor, who uses a potential that he calls the ultimate molecular Lego, which is like a Leonard-Jones potential with shape. It has ellipsoids in it. So these are decorated ellipsoids with a blob sticking out. And we use an angle axis formulation to move those rigid bodies around. And this is particularly convenient because you can code the rigid body parts once and for all and forget about it, and Doipian Chakrabarty did that. And then all you have to do to program a new system is do the site-site interactions. So the rotation matrix and the translation are system independent, and in fact you can fit all the analytical first and second derivatives on one slide. And now that you've absorbed that, I'll move on to an application. So an application, this was done with Paul Barker, who does atomic force microscopy in Cambridge. And they're interested in decorated amyloid fibers, where they put cytochromes on. I'll just show you that quickly. So here's a cartoon of an amyloid fiber with 3 strands, and the spherical blobs are the cytochromes. And they would like to make interesting optoelectronic properties out of these systems, so they would like to know what controls the pitch, because the closer you can get these guys to each other, the more likely they are to do something interesting. So, what controls the morphology of the fiber? In experiment, they see twisted and spiral ribbons like these, and kinking, depending on how they push and pull the system. And this was work done by Chris Foreman, who used rigid body building blocks with 2 ellipsoids. And so the adjustable parameter is basically an internal frustration between the 2 ellipsoids. And he realized that actually you can use this to model mesoscopic and macroscopic systems. So he went for a walk in the botanical gardens and realized that Bohinia seed pods also use this sort of mechanism. They have this morphology. That's a Bohinia seed pod. Here's the amyloid fiber and some AFM representations. And the morphology depends mostly on a couple of angles between those 2 building blocks. And in fact, you can do this macroscopically as well. So I think I will finish with one final movie. And this was work done by Szilard Fejser again. And the one thing you need to know about Szilard is he was my first Transylvanian student. So this is going to be a horror movie. It's not streaming from Transylvania, but he went to Toys R Us and he bought some buzz magnets and some putty and stuck them together with a fixed angle between, and now he's going to stack them. So his disembodied Transylvanian hand is going to appear and stack the pairs of buzz magnets into a helix. And so the question is, can our theory predict what the optimal twist angle is? Because we were doing that for the atomistic representation, well actually it's a coarse-grained representation, but actually the favored angle works for this macroscopic structure as well. And it enables us to predict both the ribbons and the kinked structures. So with that, I think I will stop, and we could do some more questions if you like.
Questions?
Yeah.
Okay, thank you for the talk. I have a couple of questions regarding the G quadruplexes that you were studying. Well, did you consider also the effect of the different ions when the molecule was falling?
No. So that is a coarse-grained model. Higher doesn't have explicit ions in it. And to do explicit ions would be quite difficult. So in fact, those structures didn't have the potassium or sodium ions in the quadruplex. And they would like to put it in. So they're trying to parameterize a version that will do that. I think actually if I really wanted to do that at the moment, I would go to an atomistic representation with amber and put in explicit ions and a droplet of water. Because if you try to do it without some explicit solvent, it probably wouldn't make sense. But the implicit model, the coarse-grained model, does have implicit solvent. It doesn't really have implicit ions. So that landscape was actually without the ions, which would help it to fold.
Yeah. Okay. And another question is, would you be able to study the simultaneously conformational change of a G quadruplex with the ligand binding?
Yes, we hope so. We're trying to do that, and we've actually been doing some work with Sir Shankar Balasubramanian and his group, where they're targeting ligands at G quadruplexes using libraries and phage display. And actually, we've done some structure prediction for ligand binding, which seems to agree very nicely with some of their results, so we're just writing that up. And in this case, the ligands are things like cyclic peptides, where you make a library with evolved mutations, and the structure prediction that we get actually seems to agree with their best mutants. So, yes.
Okay, thank you.
More questions?
Everybody needs coffee.
I have a couple of questions. Yeah.
Yeah, go ahead.
The first one is about the force fields.
Yes.
I mean, my question is, how much different force fields can affect your calculation?
Dramatically. So I was shocked by the fact that Charm and Amber disagreed for 4 alanines. And then we went on to look at the landscapes more carefully. Charm has 20 times more minima than Amber. And we don't really understand why. And it's the same, almost the same force field in terms of the representation with springs and so on. The Fourier part is slightly different, but not very different. So you would think that the charm potential had shorter range. Shorter range gives you more minima, usually. And in fact, you can write a Hamiltonian charm plus 1 minus lambda charm plus lambda amber, and vary lambda. And we've done that. And you can morph one landscape onto the other. And it's not obvious why charm has more minima, but it's some convolution of the way that the potential is different that gives you more ripples in the landscape. So I find that quite disconcerting, and I reckon, so this is why the benchmarks for global optimization, broken ergodicity, rare events are mostly atomic clusters, because we all should be able to agree on the answer for that. And if you can't do that, then you probably are going to be in trouble with more complicated things. But getting 2 potentials that agree for a biomolecule is a good day at the office.
The second question is about the computational cost of these approaches. I mean, I'm not an expert on this kind of approaches, but for example, if you can compare these approaches with, for example, metadynamics, umbrella sampling, just to get a free energy landscape, and at the level of the computational cost.
Well, this should be much faster because we're using geometry optimization. So, and I think we can use this method to guide all those sampling techniques. So the good thing here is there is no biasing. You tell me products and reactants, and we'll try and find the best pathway. And then we can take any of those pathways, and we can do any sort of umbrella sampling along them if you like. But I can show you projections that will break even the best order parameters for a simple system, because obviously you only get a lower bound to the free energy barriers. You end up averaging over different sides. And unless you have a perfect reaction coordinate, which basically means a straight line path, you average over perpendicular degrees of freedom. But this approach enables you to quantify that error, that projection error. And again, there's a benchmark for that Leonard-Jones 38 cluster that I've done very carefully. But a hybrid scheme that does this approach and then uses one of these other methods to get profiles or projected landscapes, or indeed rates using a blue moon ensemble or something for each transition state, or path sampling of any variety, or milestoning, all of those should be a good way to do it, because we should be able to characterize the pathway and the minima and the states very quickly using geometry optimization, and then we can put in any details that you'd prefer to have with other methods. So these are complementary approaches, and they should be very fast, especially the slower the process is, the better we like it. So the DNA, for example, has some extremely slow processes, which you'd probably run forever. Even with a bias, well, your best biasing method is probably just going to be wrong. You can't do a knotted protein with a biasing potential unless I tell you the pathway, and then you can. Yeah, so if I give you the union of the steepest descent paths, a purely geometrical quantity for that landscape, you can do slices and look at the distance to that and do an umbrella type sampling along that pathway, and that is a faithful representation of a free energy profile. We don't normally do that because we've got all 3n degrees of freedom. We don't need to do a projection. We've already got the rates and the thermodynamics. But we might want to get them more accurately and put in some anharmonicity. So these are complementary approaches.
Thank you.
Thank you, David. I really enjoy your talk, and thank you for the clear theoretical introductions.
And thank you for inviting me. I wish I could stay longer, but
yeah, no, it's
I'm
our
on
pleasure.
in Cambridge.
It's our pleasure, really, because it's a very clear talk and also open many avenues in that sense. I have one question. Actually, I have 3 folds, because I really understand the power, no, in geometry optimization and this kind of conformation. I would say that also for the audience, the take-home message is that the free energy surface is very rough. Okay, it's very rugged. So also the barriers that separate local minima or the global minima to the others can be very large.
Can
so
be.
in that sense, also for small systems. So I go to my question. My question is, I see you show many examples, really impressive, but I think there are a great potential, as you said, both in combining this approach with other sampling approach. It could be umbrella sampling, metadynamics, whatever you want. But also I'm wondering if such an accurate description of the free energy landscape could be very, very useful in quantum mechanics calculation for chemical reactions, in which the precision is clearly a key.
Yes.
And going on the other side of the moon, I see very powerful application for very coarse-grained models. I'm referring also to chromatin, in which you can integrate experimental measures from experiments and whatever into your models in order to guide a little bit, because of course the coarse-grained you are paying something in terms of accuracy to guide the sampling. But I would like to have your opinion.
So we're doing both of those. We're doing quantum mechanical calculations for things like ion migration and energy storage devices like batteries, so material science applications with Claire Gray's group in Cambridge, where we've explained why doping tri-positive cations actually helps battery stability in lithium batteries. And then at the other end, coarse graining, we're working with Rosanna Colapardo on models of chromatin, where each nucleosome is a bead, and on these liquid-liquid type transitions for nuclear proteins. So the geometry optimization tools should work for all of the above, so long as you have continuous energy and gradient, with a few tweaks. So the machine learning landscape is a little bit different. We needed to change the convergence criteria there. But one thing I would say is I don't like the word rough, because some people say rough when they mean lots of minima, and the number of minima increases exponentially with the number of atoms. But some large systems have simple free energy landscapes. These do. So this cluster probably has 10 to the power 55 minima, but the free energy landscape isn't rough. It's got one global free energy minimum. So when we have multiple free energy minima, I prefer to call that frustrated if there are big barriers between them, because rough isn't really defined, that's all. So all of these systems, I would say, have single funnel free energy landscapes, and you can go from potential to free energy here just by defining an order parameter that is the distance from the global minimum, and it will give you one funneled landscape here.
Yes, I agree. Even though we may also have local minimum that may play some role in terms of biology, for instance, these are not the global minimum. So it's important not to have a sample. That's the point. So global minimum, of course, in this case, in this example, very simple case, you have one global minimum, but depending, if we discuss about biological simulations, we may have higher energy minima that may play a role during the action of a system.
But something that's evolved to have one function is probably going to have one funnel. But intrinsically disordered proteins, perhaps they should really be intrinsically multifunctional proteins, and that the multiple free energy minima are selectively stabilized by some of the promiscuous ligands that they bind. What we've never seen is a glassy landscape for a biomolecule. So a structural glass with a landscape like that. We've seen multi-funnel landscapes for biomolecules, but I don't think we'll ever see anything that's really glassy in the same sense as one of these structural glass formers. So some of these ideas are certainly transferable. You just have to be a little bit careful about how you use them. But now that we have this visualization, we have a lovely way to think about it. I can't really understand anything unless I have a picture of it. We don't compute anything from these landscapes in this representation. When I'm giving you numbers, we go back to the densities of states that are all in the database, from which we plotted these graphs.
Very last comment, if I can, this is a curiosity more or less, more than other. Above all, let me make the question this way. You highlight in a couple of occasions about the necessity to have enough sampling in order to have this kind of course. So also you added that this can be a complementary method to others that can, once you have the preliminary description of the free energy. So my question is, practically in your lab, how do you manage to collect an enough amount of data in order to have a reliable description at the first glance?
Okay, so for some of the pathways, you can actually converge the rates surprisingly quickly. It depends upon the rate determining step. And although there's an infinite number of pathways, if you keep adding some of them, they're simply branching probability off the first path, and they're not significantly different. It's an ensemble of pathways. So I could, rotate a side chain somewhere in the protein, and that should really be part of the same ensemble of pathways. So if I've converged the distribution, the pathway distribution sufficiently, I should be able to get the correct rates. And that's the hardest problem. So the hierarchy is structural prediction, thermodynamics, rates in order of difficulty. And to test those convergences for the thermodynamics, we usually look at the heat capacity peaks. And then for the rates, we look at the phenomenological two-state rate constant between products and reactants. And I'm working with Tom Swinburne on a way to actually diagnose convergence more quantitatively using sensitivity analysis, where we try to estimate the effect of missing connections. So we don't know what we don't know, okay? We know what we know, and we know some of the things we don't know, and we can test the sensitivity of adding hypothetical connections that we might be missing, and then we can divert our computational effort to finding new connections for the most sensitive parts. So there are probably going to be new ways to try and direct the convergence. At the moment, what we do is extract the fastest pathway using that steady state approximation, and we look at the highest barrier, and we try and shortcut it, or we try and find minima that are relatively close but not connected, and we try double-ended searches between all of them. And we keep doing that until the rates or the disconnectivity graph stops changing, basically. So that's the pragmatic way to do it, and we hope to do something more quantitatively quite soon. That looks as though that work will actually succeed, I think. Tom is a real expert in this, so he's formulated a linear algebra representation of the problem, which we could never get to work, but he knows how to precondition it so that it does.
Here you have also a chance to see some ligand binding rates later, so maybe it could be
Yes,
inspiring for some application for you.
Yes, so we could do ligand binding so long as the ligand isn't completely dissociated. So we've done things like migration of heme groups around a heme binding protein. We're not allowed to have dissociation with extra zero eigenvalues. That, in this framework, wouldn't work. We need the most loosely associated starting point, and then we can move the ligand around. And so ligand binding, once it's already on the surface, if that is not the rate determining step, then we can do that.
Again, and now it's time for coffee break. can go on with a second speaker, that is Professor Vittorio Limongelli from University of Italian Switzerland in Lugano. That's this university. And Vittorio is going to talk about the FMAP, the Funnel-Metadynamics automated protocol for ligand binding free energy calculation. So thank you, Vittorio.
Okay, so good morning, everybody. Okay, now it works. So, morning, everybody. So we are going to switch. It's better? No? Yeah? Let's do like this. Maybe it's better. Okay, maybe it's better, right? Okay, perfect. So we are going to switch the topic from this morning lecture of David. Really enjoyed it. So we are going, I would like to give you an overview of what you can do right now in order to compute ligand protein binding free energy and different levels of accuracy. So before starting with my talk, I would like to have some feedback from you in the audience. Since I know that you are heterogeneous, because I'm one of the co-organizers of this school, I would like to know how many of you use docking to predict binding modes. Please raise your hand, because it's important for the talk to understand. Okay, how many of you use molecular dynamics or related methods like FMAP BSA to predict binding affinity? Okay, how those of you use umbrella sampling or free energy metadynamics? Only few. Okay, perfect. So it's important because I try to cover different aspects of this kind of simulations. The title is, in reality, it's related to the practical session that you will do this afternoon. I'm not going to speak about the protocol because Stefano, PhD group, Stefano Ragnolo, PhD in my group, will do this this afternoon. But I would like just focus more on the method, okay? Just to show you what you can do. Okay. So I think this is probably the most important take-home message. So if you want to fall asleep, just follow me for this slide and you can go home. So the take-home message of my talk is that life is dynamics. So, it's important to take into account the dynamical aspects of a system. Also, David showed this morning, it's very important, the free energy landscape, to understand different minimums. So system is not static like X-ray. Of course, it's important to have this kind of information, but we will learn together that it's a part of the picture. It's like to watch a beautiful movie and just a pause and see one picture. You don't understand that much from that point of view. So life is dynamic just from people that run, also cells that divide. So if you take some snapshot or as a function of the time, you can see how this process can be dynamic. And also protein, of course, are dynamic. So they have large scale motion like this door for the cyclooxygenase enzyme, or also DNA in its folding process, quadruplex. I didn't know that David spoke about that. We published this paper on Gavante about some partial unfolding, okay, of the G quadruplex. Also show that during the action in the cell, these molecules move. So the point is that it's important to take into account this motion, or to try to describe this motion with computational chemistry, computational sampling, in order to have some predictions or rationalization or experimental data. So we have to take into account dynamics. This is the take-home message. And so the point is that if I want to describe a dynamic process just by a static description of the system, the point is that, like docking, you can make some predictions, you can make some assumptions, hypotheses, about the behavior at the final effect of your system, like these fish is jumping from one body to the other. But you are doing your prediction, but in many cases, your expectation may be wrong. So in the end, your results may fail because you are neglecting important features of your system. So the point is that please don't forget the dynamics. And this is the claim of this topic. In addition, since we are discussing about drug in terms of application, it's a very complex system. So if you read this beautiful retrospective paper on Nature Review Drug Discovery of Kaplan, you understand that the drug in vivo pharmacology is by far more complex than we see together also during my talk about ligand protein binding. We are part of the picture because
If we think about our body as a simple chemical reaction, we are wrong. Just ligand with enzyme or receptor, a protein, so just a binding process regulated by binding constant, K-on, K-off, so binding kinetics. In the reality, it's not like that, because you take a drug, there is, of course, the different contribution coming from circulation, distribution, metabolism, diffusion. There are pharmacokinetics, and we don't cover this topic during my talk, but it's important to keep in mind that this plays a role for drug efficiency. And finally, when your drug reaches the disease tissues, then you have the structure there. So, of course, what we are seeing together today is just a reproduction of the interaction between a ligand and its target. But still, if we just ignore the rest and just focus only on the molecular interaction between a ligand and its protein, still the complex may be more complex than it seems, because it's not just a two bodies interaction, but you have also conformational change, induced fit effects, and so on and so forth, conformational selection. So dynamics is important, as I told you. So, but the topic on my lecture is related to the interaction of a ligand towards its target. To be not confused with the drug in vivo pharmacology. There's something, it's one piece of the puzzle, it's something more complex. Okay. We are moving this scenario. Okay, so let's focus on the ligand-protein binding interaction. The ligand-protein binding interaction, as I told you before, we can describe this as a standard chemical reaction in which we have the ligand and the protein in the unbound state. Then are at the equilibrium, we have the formation of the complex. And in doing so, we have a binding constant. That is a thermodynamic parameter that tells you how strong is the interaction between these two molecules to form the binding complex with respect to the unbound state. But also the thermodynamic property binding constant is also related to the kinetics. Indeed, binding constant can be computed as the ratio between the binding rate K on and the unbinding rate K off. If we want to put this into an artistic representation of the free energy landscape, even though this is too smooth, so sorry, David, because it's a very simple, smooth free energy surface. In the reality, it's not like that. But for the sake of the presentation, we can see that when the ligand is in the unbound state, we can consider the free energy flat, because they are not interacting, they do the two systems. When they start interacting at a certain point, so we have one more or more metastable states, we have some barriers, and then we have the lowest, the global minimum, the lowest energy minimum, which represents the so-called, for medicinal chemistry, binding mode, which is how the ligand interacts with its protein, the kind H-bond interaction, van der Waals, and we see also some examples later on. So if we compute the binding free energy difference between the bound state and the unbound state, this is related, in the case of competitor inhibitors, to the binding constant. And this is a very common and useful equation, because it allows us not only to have an estimate of the strength of the binding, because we are computing the binding constant, but also to compare in silico prediction with experiments, because in many cases, NMRists or other experimentalists are able, using also Fourier quenching, using different experimental methods, they are able to compute the binding constant. So it's a good way to compare a prediction with experimental data. So from this picture, and this is a central topic of my talk, computing binding free energy delta G, we are able to estimate the strength of the interaction, because we are measuring the gap in energy between the bound and unbound state. But this is just one piece of the story. So we are computing thermodynamics. How strong is the interaction? But how does it last? The kinetics is not taken into account, because we have to also to estimate the barrier of the free energy landscape in order to have information about one of these two guys, because once we have information or data about binding constant and, for instance, unbinding rate, the others can be derived. Okay? So the binding constant and the unbinding constant depending on the height of the barrier. Okay, we'll see in exponential fashion, in an exponential relation. We'll see later on also how to compute. It's not easy task, but can be done with a recent methodological advance. So this is the theoretical picture, no, in which we will move during my talk. There are many ways how you want, that you can represent the binding free energy. I like this one because since I'm a chemist by education, this shows how the chemical potential of the system can be taken into account, can be computed in order to estimate the absolute protein ligand binding free energy. I say absolute because we have to make a distinguish between relative and absolute binding free energy. Absolute protein ligand binding free energy means that for a single system, one ligand and one protein, I'm calculating the difference in binding free energy, absolute, between one ligand and one protein. Later on, we'll see that we have also the relative binding free energy when we compare different ligands for the same target. Anyway, you can do your job, you can do your math homework, so you can do the calculation of the potential, chemical potential for the complex, for the ligand in the bound state, and the protein in the bound state, making the ratio, also taking into account rototranslation degrees of freedom, you can compute this binding free energy. This is very well explained as different reviews. One is also coming out, hopefully very soon. And so this is the second take-home message of my talk is, since you raise your hand, so I use docking, I'm using MD, I'm using PBSA, so on and so forth. The question is, which method to choose? Well, in my experience, the rules, I only know 3 rules that are always true. That is, no method supersedes the other. So there is no method better than the others. Depends on what you want to do. The other common rule that is the only one that is always true, that I always find to be true, is that the accuracy is always traded for the speed. So if you have a very fast method, this is generally less accurate. If you have a very accurate method, generally it's lower. So depending on what is the task of your research project. And in the end, consider the first 2 rules, you have to choose the method based on the goal of your research. What does it mean? This means that if I have, for instance, to screen millions or billions of ligands, as we have seen, beautiful examples in this course by Ruben Abajan, and also Alexander Bonven show many beautiful examples in that sense. Of course, we have to pay some in terms of accuracy because we cannot study accurately 1 million of ligands, and by even 30,000, whatever. So we have to go through fast methods like molecular docking, and we have seen ICM, we have seen IDOC, we have seen many kind of these examples in which you can describe roughly, but still at a reasonable level, the interaction between a ligand and its protein. On the other way, if you want to study in a more accurate way the ligand-protein interaction, for instance, you have to study 10 ligands, now also 20 or 50, because there are examples in which also an important number of ligands can be studied through these methods, you can go for more accurate simulations that have at the base molecular dynamics simulations or Monte Carlo calculations. And in this, using this approach, of course, because of the time scale issue that we'll see in the next slide, you can also choose some free energy methods, depending also on the task, as we said, of your research. So we can go towards the endpoint methods like the line method of Oquist and PBSA, or pathway free energy methods that includes free energy perturbation, thermodynamic integration, Bennett acceptance ratio, umbrella sampling, steric molecular dynamics, and Funnel-Metadynamics. That is the argument of my talk. And I'm really glad that yesterday Vitas introduced very, very well this part, because this allows me to save some time and go directly to the point. So the next 2 slides that I reduced very much because Vitas yesterday already introduced you to this topic, is just to give you an overview of the method available. Endpoint free energy method, why they call like that? Because you do simulations of the complex, so ligand and the protein, and in waters, of course, and the ligand only in waters. And when you do that using the linear interaction energy method, all the related methods that are similar to this, but this was the reference one, you can compute the average of the electrostatic interaction between the ligand and its environment, okay, in this case the solvent. So you can do this for the electrostatic part, you can do this for the van der Waals part, and you can correlate this to the binding free energy using these parameters alpha and beta. There are experimental or empirical parameters. What does it mean? This means that this method neglects many degrees of freedom. So you need some experimental data in order, at least a couple of experimental data, in order to have a correlation between the computed binding free energy through this formula and the experimental data. So you have to calibrate your calculation. In doing so, you are setting the experimental parameter that allows you to take into account the degrees of freedom that you are neglecting in this kind of calculations. And this is the line method, for instance. And the other method is molecular mechanics post-Boltzmann surface area, or the variant generalized Born approach, It's still related to these core endpoint methods because we are considering the end point, the bound and unbound. In this case, you have also to add the protein in water simulation. So you have 3 systems: protein waters without the ligand, protein with the ligand, and the ligand in water. Then you strip out the water, so you remove the waters, and you do some kind of estimation of the free energy for the bound, electrostatic, van der Waals, and you also compute the solvation free energy in terms of the polar form using Poisson-Boltzmann or generalized Born approach, and the non-polar using a linear relation to the solvent accessible surface. And also you can take into account the entropy. Some studies do, sometimes not, depends. You can use normal mode analysis to do so. In the end, you have an estimate of the free energy, and in doing so, you can do an average. You can estimate an average using the frames of your simulation in order to get an estimate of the binding free energy. Also in this case, there are properties of the system that are neglected because, of course, as I told you, this is an implicit continuum solvent model. So this means that the enthalpic and entropic contribution of waters are not explicitly taken into account. And this also, of course, represents an approximation in the estimate. So in the end, what happens, also considering the way of including the entropy effect in this estimation, usually it's overestimated the binding free energy, even of 10-fold overestimated. So what happens that if you want to compare binding free energy computed by this method, you can use this for structurally similar ligands. Okay, you need to have at least some experimental data in order to calibrate also in this case the comparison between the ligands that you have studied towards your system and the binding free energy that's been computed using the experiment. And if you have structurally different ligands, you may be in trouble because of this inaccuracy that you have in this estimation, because you may find that some true positive can become false because of this contribution that you are neglecting. So the suggestion is you can use this method because are very fast, are very user-friendly, so many people continue to use that, but only if you want to study different ligands towards the same target. And it's also difficult, I tell you, to compare results between different groups that are studying the same systems, because they use different approximation when they found this, they do this kind of calculation. So pay attention, use them, but carefully. On your own, you have congeneric series of ligands. For congeneric ligands, it may work in order to have a correlation to say, okay, this functional group, I added this functional group to these atoms, is better or not. You can do this kind of qualitative, I would say qualitative comparison, but don't believe them much to the number, because as I told you, you may be in trouble. Okay. So there are other methods that maybe are more accurate than the previous that I showed before, like the alchemical pathway free energy method that we have seen yesterday, the thermodynamic integration, that can use the discretization of the Hamiltonian. So you have lambda, you set lambda from 0 to 1, so you can just simply reproduce the system in the bound state, and then the ligand in the bound state, just switching off and on. First the electrostatic, then the van der Waals, so this kind of interaction. In this case, you should be very careful in make a discretized lambda, as we showed yesterday. We can compute the average of the Hamiltonian, and so on and so forth. In doing so, if you do, anyway, an appropriate calculation, you can get a reliable and accurate estimation of the absolute protein binding free energy. Okay, this can be done using the thermodynamic integration. You can also use the Bennett's-exception ratio that is even more reliable, I would say, because it requires less sampling with respect to the thermodynamic integration, but still you are in the field to have a decoupling, I would say, okay, a decoupling of the interaction forces between the ligand and the protein. Another methods that are in this group is the so-called free energy perturbation. Now it's very, I would say, trendy, also commonly used, because there is this also FAT plus automated protocols that was published some years ago, a couple years ago on JAX. So at the base, you have the Zwangen exponential averaging equation, in which you can compare the difference in free energy between two ligands in this case, as making the average of the difference of the potential energy. What you're just exploiting is a thermodynamic cycle like this, in which you have ligand A bound to the protein, a ligand B bound to the same protein, and you just compute, as you see here, the relative, so no longer the absolute ligand binding free energy, but the relative binding free energy, just counting the binding free energy for B, for the ligand B, minus the binding free energy of ligand A, and just make this equality with the transforming ligand A into ligand B. So in doing this transformation from one system to the others, you can compute the different relative difference binding free energy. Okay. So this method works quite well, it's very reliable, but you can use this kind of calculation if you have very structurally similar ligands. So when you have to permutate, when you have to do this kind of perturbation from ligand A to ligand B, necessarily the two ligands should be so very close. So you can add 1, 2, 3 different atoms, not more. If you pass from a neutral ligand to a charged ligand, you may be in trouble, so pay attention to this kind of transformation. So it works, I would say it's reliable. It's reliable. You can do this. Also, you need some time to converge. So an advice that I may have for you is to check that the forward reaction going from A to B is equal to the backward reaction of ligand A in order to be sure that you are taking into account, you are converged properly your calculations. But the point is that these are reliable methods. But as I told you, we have some limitations because we need to, first of all, the first prerequisite is that we need to know the binding mode. If you don't know the binding mode, you cannot apply this technique. And then once you know the binding mode, you can compute the relative binding free energy or the absolute binding free energy using this technique. Okay. There are also other examples of methods that can be applied to study ligand-protein interaction, like the physical pathway free energy methods. The most famous one, and maybe the oldest one, is umbrella sampling. It was originally published and reported by Vittorio, and we already saw it also yesterday, the introduction to this method. You can compute the distribution using an umbrella restraints, and once you have a distribution, you can reweight the statistic, using some basic statistical analysis. You can reweight the distribution considering the umbrella restraint and finally get the potential mean force that tells you potential mean force because you get an average of this distribution, then you reweight the distribution to get the final free energy that it's interest for you because you want to have the difference between your bound state and your unbound state. You do this calculation, you can parallelize, so it's the good news. You can run in parallel, so you can run all these umbrella simulations in parallel, and then you just collect the data and do your post-processing analysis to get the final PMF calculation. Still, it's a good technique because you are exploiting, you are sampling the physical pathway of ligand-protein binding. This is a good news with respect to the others. On the other way around, you have to choose a reaction coordinate. As also David said, most of the cases just a line, just the distance between bodies. I want to study how my ligand gets into the protein, just draw a line and use this as a reaction coordinate. It's quite rough because, as you can imagine, the degrees of freedom are several, so it cannot be represented by simple one reaction coordinate, and this may affect the convergence of your calculations. In this case, you have to check, to do many post-processing analysis in order to be sure that your calculation not only converge, because the point is that umbrella sampling can converge, but can converge to the wrong value. So it's not self-diagnostic, I would say. Another method very commonly used, also because it's user-friendly. People love user-friendly methods because already implemented in MD code, so it's very fast. Just run the input. It seems some tutorials. It's good from a set point, but it's also can be risky. The stereomolecular dynamics, in which just a pulling force is applied to a ligand to separate this from the protein, and then you can recompute the binding free energy, the difference in free energies, then just computing the work done, and also taking into account the dissipative work you have to subtract, because the average of the work that you do in this kind of pulling trajectory is related to the difference by difference using the justified equality, but also have a look to the Crookes theorem because the two things are very interconnected and explain you how this equation holds. Okay? Oh, in this panorama, what I would say, so I have a first question for you, ligand-protein binding. So what method you may use to compute relative binding free energy? If I have this binding mode that is supposed to crystallize or whatever you want, I want to make this derivative because I'm collaborating with some experimental synthesis guy, okay? They asked me to improve, do lead optimization. So this means having a scaffold and modify the scaffold in order to improve the interaction of a ligand with its protein. Okay, you design this because you think that this is an arginine here, so you can make this salt bridge interaction, it makes the ligand stronger. Okay, which kind of method you may use? After this brief overview, in your opinion? Please, make a guess. Okay, free energy perturbation, it's the answer. You can use free energy perturbation, you can use thermodynamic degradation, you can use Bennett exception. Actually, I commit a mistake here, a typos, but you can use also Bennett exception ratio, and this provides you a reliable estimate of the binding free energy. But you are rely on two factors in this case. I would say free energy perturbation, you may be in trouble because it's charged and it's not, first of all. Secondly, so I can find many pitfalls as for you. Secondly, you are supposing that structurally similar ligands bind similarly. This could be not the case. Thirdly, also the arrangement of the residues of the protein may change passing from one ligand A to ligand B, and this also can be not taken into account easily in very short simulations. You have the time scalation when you do this simulation with free energy perturbation to get this conformational change of the protein. And you are still more in trouble if the protein passing from ligand A to ligand B has some larger conformational change. A loop like that, for instance, that move a little bit. If you don't take this into account, of course, your calculation gives you a wrong number. Okay, so it's good. The conclusion by base, anyway, should be careful in doing so. But what if we don't know the ligand binding mode? So we have the protein here, but the binding mode, the binding site, we know where is the binding site, more or less, but we don't know the binding mode. You are in trouble. You can use docking with all the problems in accuracy that we know. So the topic of my talk is to show you that this is possible with Funnel-Metadynamics, that is similar as a physical pathway free energy middle, so can be compared to umbrella sampling or stir molecular dynamics, but still we have some, I hope that I convince you to have some advantages, no, with respect to the other methods. So the outline of my lecture is simply to introduce the method here, also how we develop the methods in the years, from the first application of metadynamics to ligand protein system, and then the step forward towards Funnel-Metadynamics. And we see that we are able to describe the binding free energy surface for different systems, also to get information about ligand protein binding kinetics, so the off-rate in this case is binding kinetics, and finally, I don't think I have time, but the Funnel-Metadynamics automated protocol is the argument of the practical session, and Stefano will introduce you to this. So you can find some reference here if you want to have a look how this method has been first developed in this original paper on PNS in 2013 with also Michele Farinelli and Massimiliano Bonomi, but then you can find many other applications by my group, also by others in the literature. So molecular dynamics, actually, I think, I don't know, I make a guess. Helmut Grumüller is coming. I think Helmut will give a lecture on molecular dynamics, so I don't want to spend so much time on that, because yesterday Vita just introduced quickly molecular dynamics. Suppose that most of you already know. It's you use the Newton equation of motion, so you move your atom, you compute momentum, you can accelerate your system and compute the trajectory in a deterministic way. To use that, you can compute the forces, the derivative of the potential energy with respect to the coordinates. You apply the force to your atom and the acceleration, so your atom moves. That's why molecular dynamics. And what do you use to evaluate the potential energy? You use a master equation. The standard common one is the master equation of the force field that allows you to compute the potential energy, take into account the different contribution for the bonding and non-bonding interaction, in which in the bonding interaction we have the so-called Lennard-Jones potential, so the van der Waals interaction, atom-mass-mass, atom-atom interaction, and the Coulomb equation in order to take into account the charge, the short-range charge interaction. Okay, I don't want to enter into these details. Are quite standard stuff. You should know Lennard-Jones is here. You have also here you have also the H bond here in this type of force field, number one, and this is the Coulombic part. Okay. So the point is that molecular dynamics let move the atom. So it's enough to let move the atom. I just start my simulation from frame zero, give a kickoff, and let's see what happens. It's enough to see what happens to describe a ligand-protein interaction. Unfortunately not. Unfortunately not, because even though David somehow doesn't fully agree, the face is rough, it's very rough. We have many valleys, we have many peaks. So it's very difficult to understand where we are. Suppose that our free energy, this is a binding free energy landscape of a drug to cyclooxygenase, okay? And as you can see here, this can be compared very well to EPS landscape. So we have different wells, different basins, and we have to jump from one basin to another one can be very complex, may take into account several degrees of freedom, and to do that, you need time. You need time because as I told you, to cross energy barrier, this is exponentially proportional to the higher the barrier. So this means the probability to cross the barrier is very low if your barrier is very high. Okay. So in the end, what happens? If you start your simulation from which whatever conformation you want, from a docking calculation, you have your ligand, your protein, you did your docking calculation, and start from that pose, you may get stuck. You just get stuck in a minimum, and you may stay there for a long time, also for all your PhD study, and you never find that your ligand is able to cross the barriers that you are necessary to explore in order to have an exhaustive sampling of the free energy surface. Okay, you have the protein, the binding site here. You want that your ligand explore the binding site to understand which is the most probable, not the lowest energy pose in your free energy landscape. So there is a time scale issue. There is a time scale issue that nowadays allows also to reach 10 microseconds, I would say, of simulation thanks to the increasing computing power, but still it's not enough because biological process like ligand binding, but also protein folding happens also in the second minutes time scale. So you are not able to do that in a reasonable computing time so far. So if we see this slide, you can understand what I'm saying, that depending on the size of your system, the time scale of the phenomena that you want to study, you may choose the most appropriate approach. You can pass from the Schrödinger equation, so the quantum level, so quantum mechanics, if you want to just describe very small system, 10 to the minus meter scale, and for very few, for very short time scale processes. And if you want to do something that is in the microsecond time scale with a larger system, you can use molecular dynamics, then you go for Monte Carlo. If you want to describe more complex system made by several molecules, proteins, for instance, think about a cell section, a membrane plane with different proteins interacted to each to the other, of course, you are not allowed to do that with the atomistic representation. You can go for coarse-grain representation, also to the mesoscale if you want. So the time scale and the length scale are in relation linearly, and you have to choose the method based on the research goal that you have to pursue. Okay? So since there is a time scale issue, so using atomistic molecular dynamics simulation, we are not able to describe such a long time scale process. We need some trick. And the trick is basically achieved using a dimensional reduction. So while in standard atomistic molecular dynamics, you have a macroscopic variables who is the atom coordinate x, y, z, so in the Cartesian space, and you do your Newton dynamics following the Newton equation, and you can compute the forces, the trajectory, the position of the atoms, so on and so forth. Well, it's good to have a description, a coarse-grained description, I would say, even though it's, I don't want to confuse you, so call it collective variables description of your system. What does it mean? That if I want to describe my body motion, instead of describing all the atoms that are moving, I want to describe this motion, instead of describing all the atoms that form my arm for the motion, I just describe the distance between my shoulder and my hand, and just describe this distance, I'm able to describe this phenomenon. Okay? I'm using a collective variable to describe a motion. I can do that also in another way, more accurate, using all the atoms, but it takes more time. It's the same approach, generally. So you can do this, and then in the end, you can use Ligand dynamics in order to compute the free energy as a function of these collective variables that you have to choose. That this is a critical, a key step when you do this kind of calculation, because if you choose the wrong collective variables, you do not converge, as I'll show you later. Okay, so the major advantage of this approach is the analysis of the Q space, because you can go back to the atomistic description of your system by means of modeling dynamics in the S space. So I use collective variables to make the action, but I have information about the atoms, so at microscopic level. So in the end, this is how metadynamics work. So if you run standard molecular dynamics, you get stuck in a minimum. If you metadynamics, you add an external potential with the shape of a Gaussian, and you can define, the user has to define the width, the height, and the piece, so the position stride of the Gaussian. And in doing so, you add many, many Gaussian to your local minimum, that in the end, you are able to cross the barrier and go in another one. So you see in this movie here. So you go forward and back several times during your simulation, and you know the amount of potential energy bias that you have added, because you have defined the Gaussian dimension. And if you look at the paper that introduced the method in 2002 by Michele Parnello and Sandro Laio, you can understand how this method works in details. I don't want to spend much time, but just to show you the basic theory behind that. It's not so complicated, actually. So you have the potential you add to your collective variable as a function of the collective variable at the time. You have the width of the Gaussian that you have to your system. You have some energy rate, which is the height of your Gaussian divided by the pace, the time at which, the frequency at which you add this potential to your system. And then you get, in the end, your potential using this, making this integral. And once you converge your simulations, your final free energy is related to this potential plus a constant, because you are overfilling the basin. So if you go back to the movie, here, okay, you see that you are here, so your free energy is equal to the yellow surface that you add to your system plus a constant, because you continue to go forth and back, so you have this constant that you bring with you and you can recompute. This was the original method developed in the so-called standard metadynamics in 22. But later on it was thought that it's better to try to converge better the calculation, so it was developed the well-tempered metadynamics, in which you can compute the rate at which the potential is added to your system, the decrease with slow. So if you add as your simulation proceeds, your metadynamics bias grows, the rate of the deposition of your bias decreases. In doing so, you are adding less and less bias to your system in the end. So you cross the barrier, but in the end, you are reaching a convergence in which, in the end of your simulation, the dimension of your Gaussian is very, very small. So your system proceeds in a semi-diffusive way. You have the bias underlined, but you are in very, very small hills, very, very small Gaussian with respect to the original method. This allows you to converge faster, allows the error to be dumped out, so you reduce the error of your calculations, and you have many, many, many advantages in using this method. There are some parameters to set, like the bias factor, this delta T, the unit of temperature. And in the end, you get the potential that you compute using well-tempered metadynamics is proportional to the free energy using this constant. This is a constant because T is the temperature of your system. Delta T is the difference between the temperature of your CV, this bias factor, and the temperature of your system. So this is a constant, and it does not change once you set this parameter at the beginning of your simulations. And at the end of your calculations, once your calculation converged, and later on I show you how to check the convergence of this kind of calculation, computing this potential you add to your system, in this case is the yellow surface, and this constant, you can compute the free energy. Okay, so far so good. Any question? No? Clear? Perfect. So let's see some applications. So I told you that, of course, the key point of this kind of calculation is to set up the collective variables. So the bad news is that you have to describe a very complex process like the ligand-protein interaction, like in this case, cyclooxygen is an important inflammatory target. So most of you have, of course, in your pocket aspirin or ibuprofen or paracetamol, all these target this protein, so it's important pharmaceutical target. We studied in one of the first applications of metadynamics to this kind of system in 2010. On PNS, we published this paper in which we describe the different binding behavior of a selective drug for the COX-2 isoform with respect to COX-1. For several years, medicinal chemistry tried to find selective ligand for this target because this is induced when you have an inflammation, why this is a constitutive. So we don't want to inhibit a constitutive isoform, but just those that is induced after inflammation because it's selective. So if you have pain, if you have a rash, this is expressed. So if I selectively inhibit this one, I just inhibiting the inflammation site and not the other tissues in which you have the constitutive expression of the COX-1. Anyway, this is the biological point of view. The point is that it is very hard to describe this kind of interaction. So choosing the CV was not easy at that time. But the good news is that the simulation converge only if you choose the good CVs. So if you choose a bad CV setting, in the end your simulation does not converge. good, an advantage with respect to other methods. Anyway, when we see the free energy surface that is described as a function of a torsion and a distance, the distance is the distance between the ligand and the protein, and the torsion is the different orientation of a ligand with respect to the protein, we may find that in the bound state, so when the distance between the ligand and the protein is lower than 10, and we also look at the torsion CV, so a different orientation with the ligand with respect to the protein, we found two minima, A and B. One was an X-ray pose, the other one was a second minimum. And indeed, it was quite new because at that time, it was known that this drug was able to bind to the cyclooxygenase only in one binding mode, also according to the X-ray structure. And the second one was never discovered. Even though there was this very old study in which this guy, Lanzo and others, found by fluorescence quenching that they have a double signals when the ligand is inside. That means that there are at least two stable states, not just one. So this means that there should be another binding mode, not only one. And it was that one that we found that when we compare this binding mode that we found with ibuprofen drug, it's a commonly used drug for anti-inflammatory reason, co-crystallized COX-1, we will see that the intermolecular interaction between the drug and the ibuprofen were very similar. So you can see here the interaction with this arginine are reproduced by the sulfonamide group, and also the hydrophobic interaction with the phenylalanine 518 is reproduced also here. So in the end, what happens is that if we do the calculation in COX-1, we see that we have one free energy minimum, while in COX-2 we have two, and the fact that in the COX-2 we have a lower binding, a lower basing with respect to COX-1 means that it spend more time. And that way we were able to at least qualitatively explain the selectivity of this drug in this target. But this happened in 2010, and if I tell you the whole story, this was one of the first applications for this kind of complex system. The simulation lasts only, if I'm not going wrong, only 80 or 100 nanoseconds. It was nothing. The simulation, I may say, maybe are not properly converged, but we have a qualitative description of the free energy landscape. And the point was that when I used to run this kind of calculation with metadynamics, when the ligand, for several systems, when the ligand leaves the binding site, it goes out in the bulk, in the solvent, here in our simulation we have explicit solvent models. So we have also water molecules that are not displayed for the sake of clarity. When the ligand is here, it is able to go around the surface of the protein because of the entropy, because of the different interaction site, and this affects the convergence. In doing so, I don't see the forth and back events so many often, and this, of course, affects the quality of the free energy landscape. In the end, I have a free energy landscape that is not well characterized, a quantitatively well characterized. What happens, as you can see here, it is in the bound state in which there is no contact between the ligand and the protein, the free energy landscape is not flat as it's supposed to be. Because here, as a function of the torsion, the orientation of the ligand, any position in the free energy landscape should be position and rotational independent, because the two bodies, the two molecules, protein and ligand, don't feel each to the other. So this should be reflected by a flat free energy landscape. The fact that you have some basins here, this means that you have reached some places, but you have not exhaustively sampled the whole unbound state. So an idea that came to me just reading literature, as always, inspiration comes from literature. Another important message for you, read the literatures, because if you have a brilliant idea, in many cases, some others already did it, but you can start from some important piece of work or other groups and try to apply or to improve what has been done to your system. So what we thought is that if we apply a funnel-shaped external potential to our system that just include the binding site, and in the unbound region it has a cylinder shape, in doing so we are restraining the central mass of the ligand inside this funnel, and you can customize, you can tailor the shape of your funnel depending on the protein you are studying, using a couple of parameters: the amplitude of the cone sections, the radius of the cylinder, and the point to which you want to switch from the cone section to the cylinder section. Okay, it's a very simple idea, and the most important thing is that we add an external potential that is affects the system only when the central mass of the ligand touch the edge of the funnel. So as long as the ligand is inside the funnel, no external potential is felt by the system. Okay? So this means that when the ligand is here and exploring the binding site, It works as a standard molecular dynamics, metadynamics, whatever you want to combine with this kind of approach. But as long as the central mass of the ligand touches the edge, it feels an external potential that, of course, constrained in this shape. So remember the formula that I introduced you about absolute protein-ligand binding free energy, the binding constants. Using some basic math, also inspired by the work of Benoit Roux in the past about some cylinder construction to compute the binding free energy for umbrella assembly simulations, you can compute the binding free energy, you can compute the binding constant just given by this integral in between the potential of mean force in the bound and unbound state. If you have some influence of your external potential in the binding site, you should take this into account. But if you properly chose the amplitude of your convection to fully include the binding site, this contribution is equal to 0 because there is no effect of your external potential into the free energy value that you are collecting in the bound state. So you're just computing the difference between the free energy between the bound and bound states plus an analytically correction value that takes into account the entropy cost to constrain your ligand into the cylinder section instead of go everywhere in the box. And indeed, this has the shape of Greek pi, the square of the radius of the cylinder you apply to the system. Making this analytically correction, you can get finally the correct value of the binding constant. So how the simulation works, you can see here, Funnel-Metadynamics applied to benzene trypsins, a toy model to demonstrate that the middle works. It seems that the ligand is fully free to go everywhere. In the protein, everything is fully flexible. The protein can rotate and translate, but in the end, it's not like that. As you can see here, the central mass of the ligand is constrained inside the funnel, as I told you. So in doing so, you can sample a large number of binding and unbinding events because the ligand get out and get in several times. And at the end of your calculations, once your calculation has converged, you can have a reliable, quantitatively well-characterized description of the free energy landscape. And this is exactly, you can find the tools on my website, but also later on I've introduced also the Puma Nest. There's a new consortium in which we also deposit the protocols, the data, and all the things to do. If you want to do, you will have a try. You just download this from the website, but we'll see in the afternoon how you can do that. So the difference between the previous free energy, I think it's quite intuitive, okay? In the unbound state, look how flat is the binding free energy. This means that you converge. This means that you go forward and back. It's not the only analysis you have to do to check the convergence. To check the convergence, you have to check how the heat decrease. Your system continues to go forward and back during your simulation, even after the convergence. This means that you are in a semi-diffusive way, so you're going in the bound state, and your RDC converge, and your free energy landscape is not changing after your convergence. You continue sampling, and your free energy converges towards a value, okay? If you do the calculation of the binding free energy. So if you compare the unbound region in this simulation of Funnel-Metadynamics with the previous unbound region obtained with no Funnel-Metadynamics, you see how the difference is clear. And this is because it's the unbound states, as I told you before, must be position and torsion independent, as it is in this case. And you can clearly identify the ligand binding mode or binding modes, as in this case. And you can retrieve all the information about the intermolecular interaction between the ligand and your target protein, including the rule of waters, because the waters are taken into account explicitly. And believe me, in most of the systems that I study, waters play crucial roles. Neglecting waters may affect a lot your results, not only quantitatively, but also qualitatively. If you look at, I didn't mention, but you can read the paper if you want. I don't know, because it does not go back. That finally, you just, to compute the binding free energy, take the difference between the lowest energy minimum with one of the energy states in the bound state, because it doesn't matter, they are the same energy value, makes the difference plus the analytical correction due to the presence of the cylinder, that is depending on the radius, in this case 1 angstrom, to constrain the ligand in the bound state. You make this calculation very simple, and you get the final binding free energy with a low error. The lower error means that method is precise. This is a numerical calculation, okay? It does not mean that your free energy is in the range, because the force field inaccuracy is larger than the statistical estimate of the error. This solo statistical estimate of the error means that your method is precise. So in doing so, at the end, you have a convergent number within this range. But please take into account another important message for you, that the force field for protein, this kind of interaction, today are estimated to be in accuracy range of 1.52 at least kilocalories per mole. So this, of course, should be taken into account when you perform every kind of atomicity simulations. Anyway, this is falling the range of previous estimates, so it was nice. But it's also very nice to compare the waters found by Funnel-Metadynamics with the X-ray waters. It's important, you know why? Because your system can start from the unbound state. So there's no constraint on waters, protein, or whatever. So this means that in doing so, if the water motion are fast, because you are not including this in the collective variables, you are able to retrieve, to recover the right position of the waters. And also, this water made some important interplay rules in making water bridge interaction between the ligand and the protein. So it's important also to keep in mind that we not only take into account the protein flexibility, the ligand flexibility, but also the water motion in our calculations. Then the question could be, okay, yes, but for a very complex system, it's difficult to describe a ligand-protein interaction just merely between a distance and a torsion, or you can add some extra things that I'll show you later, content map or other things. So we want to include more description, or try to not to have a general receipt, but to have a more appropriate description of the ligand-protein binding. Well, in this nice example we just published this year, it's called VAC-FM, so Variational Approach Conformation of Metadynamics applied to Funnel-Metadynamics. That is originally is a variant of the time lag independent conformation analysis in molecular dynamics developed by Frank Noe and Peter Andersen. You can see that you can define a number of descriptors, general descriptors of your system, like in this case, number of contact between the protein and the ligand, number of waters in the binding pocket, a torsion that describes the orientation of the ligand with respect to the protein, and number of waters around the ligand in order to describe the solvation of the protein binding site and the ligand binding site. And if you do some analysis of your trajectory, preliminary trajectory, you can compute the covariance matrix and you can have this generalized eigenvalue equation that correlates between the covariance matrix at time 0 and time lag covariance matrix, and you can compute using this equality, which is the weight to apply to this linear combination of the different descriptors that you have defined for your systems. If you do this analysis, you will define that the slowest decaying ng values ng vectors are those that play the measure rule, as is expected. So it's a kind of most of you maybe already tried PCA, principal component analysis. It's a variant of doing this kind of calculation, I would say. Okay, so if you do this job, in the end you can have a linear one single CV that takes into account several description by means of a weighted linear combination. And what you can do, you just simply sampling two CVs that includes many descriptors of your system, you are able to recover on the same system, the benzamin trypsin, the same binding modes that we have found using our original approach. But we were able to converge our calculations in 300 nanoseconds, while before we need 500 nanoseconds for a simple system like trypsin benzamide. So this means that you can converge faster because you take into account properly this thing, and you're also weighting the contribution of a different degrees of freedom or proprietary if you make this analysis. Okay, I hope that I convinced you that Funnel-Metadynamics at least it's worth trying, but if you have still some doubt, please see this predictive power in which we predict before the coming out of the X-ray structures, we predict this binding model for this ligand in the cyclooxygenase by Metadynamics, and when it was published, the X-ray structure was amazing. The overlap is below 1.2 angstrom. I don't remember the exact number, but you can see here it was exactly the same, the binding mode that we predict, and there was no information before about the binding mode of this ligand in this isoform of cyclooxygenase. Okay. So far we've seen the thermodynamics. I want to check the time. But I told you also that it's already 12 actually. I show you the kinetics and just make a break. I'll show you more application later on. So I told you also that kinetics is important, okay? Kinetics is important because drug works only as long as it is bound. So it's important to account for the residence time of a ligand. We have seen that we compute the binding constant. Binding friendship means the difference between the bound and bound state. But what about the kinetics? How we can estimate the unbinding rate, the time necessary for ligand to leave the binding mode. Well, this is extremely important topic. You may say, why K off and not K on? Well, you can compute both because you need just one of the two. But if you also have a look to this review already introduced before of Copland, but also Alexander Bonvin introduced some slides in which he showed that the efficiency of drug protein binding, the KD, the dissociation constant, is 1 over the binding constant, is proportional to the K off, while there is there's no relation between the K on. So it seems that the binding rate is related to better to the drug in vivo efficacy with respect to the K on. So K off is something that is supposed to be important to compute, to take into account in order to have a good estimate, a perfect drug in your hands. If you are able to describe accurately, to calculate accurately the binding constant and the binding rate, you have in your hands the perfect tool to develop the perfect drug. A drug that is bounds faster, stay very strong interaction, so very deep energy minimum, and very long resident time. Not too much, because otherwise you may have side effect, like in the opioid case, where you have so potent drug that cannot be used in humans, because otherwise you kill the patients. But still, it's important to have the tools to tune, okay, this resident time. And this is what we did. That it was very nice. They also did show acknowledge. Oh, sorry. No, I did like. Okay. Also, this show in this drug discovery today paper in 2013 also acknowledge that for the K-on, also brute force molecular dynamics can be used, but for the K-off, for the unbinding rate, because the ligand dissociation is lower, often taking seconds to hours, it can usually be observed computation only by use of these later techniques, as later techniques they mention enhanced sampling simulations. So still time scale issue. Still we cannot use brute force MD, as also written by this show. We need to enhance the sampling. Otherwise, we cannot do that. That is something that we do in this PNS paper, a couple of years ago, with also Pradesh Tiwari and Matteo and Michele Parinello. And what we did here was infrequent metadynamics. What we did is, okay, we don't want to have corrupted dynamics. So what we can do, we can apply the metadynamics protocol, so we can accelerate the sampling here with Gaussian, but with a very slow deposition rate. So the frequency at which I put the bias, I put the Gaussian to my system is very large. So the time interval. So in the end, what happens that I can cross the barrier without adding any metadynamics bias to the barrier. In doing so, what I observed is a transition time in the metadynamics regime, and I compute the acceleration factor that is given by how much bias I've added to my basin in order to cross the barrier. If I compute the acceleration factor using this average estimate of the bias that I put in my minimum to cross the barrier, and computing the simulation time when you do metadynamics to cross the barrier, you have the real time of the transition that is given by the acceleration factor times makes the product of the acceleration factor with the metadynamics time in which you observe the crossing. Well, this is a powerful method, but you have to be sure that you have not added any bias in the transition state. Otherwise, you are in trouble because you are corrupting the kinetics, because you have bias there, so you're accelerating the transition. And you don't want that, because still you want to have a process Markovian somehow when you cross the barrier, okay? So in doing so, you can compute the theoretical cumulative distribution function of the event of crossing a barrier, and your experimental one based on the calculation of the rate that you did in your calculation. You run a number of simulations in parallel, and you compute this estimate several times, and put this in your graph. In the end, you can compute the p-value using this Kolmogorov-Smirnov test, and in doing so, you can estimate the p-value that tells you if your transition is Markovian or not. Is your transition has been not corrupted, is not affected by the bias you added or not. In addition, you can also check with this p-value if your choice of the corrective variable has been correct. Because if you chose a bad CV setting, you will have a distribution that is not very close to the theoretical one. So when you do this kind of a posteriori check of your transition, you can check, you can do your job, and you say, okay, I chose the right CV, and my transition is correct. So let's move on. let's move on. What does it mean? That I can identify different basins, different intermediate states or lower global free energy minimum in my system, and then I can compute the rates between transition between the different macro states that you can identify. You can develop basically a macro state models. You can do a flux analysis, kinetic maps that allows you to give you, in the end, the K-off rate of your binding event. And if you see, as I showed you before, the estimate of the binding rate is a reasonable agreement with the experimental value. But the most important thing is not only the number, because the number, again, may be affected by the force field inaccuracy, whatever. Still, it's important to understand that you are able, during this calculation, to really identify the rate limiting step of your unbinding. So, which is the transition state that affects the ligand binding from its molecular target. So in this case, in the case of trypsin benzamidine, passing from state A to state B, we have the transition state A to P. From state A to state B, we have transition state A to B. And we can get the atomistic structures of the transition state, in which you can define not only the, again, all the interaction, H bond, hydrophobic contact between the ligand and the protein, also the rule of the waters. And this is extremely important because these are high energy states that are elusive to any experimental methods like X-ray and MR, because these are high energy transient state that just lives for a while, and you have to catch it in the time. So how to be sure that these are transition state? Once you have identified the structure, you can do some commuter analysis. So you start a number parallel simulation, molecular dynamics, no bias, and see that you should have a half distribution that goes in one minimum and the other half that goes in the other. Right? So if you do so, you are sure that your simulation, your transition state is exactly the set of points that you identified. In doing so, you can also estimate the unbinding rate. So you can say that in 83% of the cases, the ligand exits from this site, and the 70% out of 100 cases, it goes from P. So you can estimate also the unbinding pathway of the ligand from its target. One may say, okay, come on, but this is a very simple system, even though believe me, this is not so simple. Trypsin benzamidine, people think it's a toy model, but still you have proteins with many side chain problems, also some kind of conformational change. But still, let's say the benzamidine is very rigid. The protein is softly exposed binding site. It's too easy. Yes and not, I would say, but we proved that this method can be applied also to some drug-like molecules. Sorry, but it just gets stuck like molecular dynamics. My remote control is not going on. I don't know why. Maybe, sorry. Anyway, we demonstrate, it's very weird. Let's go directly to the next slide manually. It's better, okay. So we demonstrate that this can be done also for a more pharmaceutical relevant system like the P38 MAP kinase for a drug-like molecule like this one with some experimental value for the binding rate. And we again here in this JAX paper 2 years ago, we demonstrated that from the binding site we can have different metastable states reaching the final unbound state, and the rate limiting step is transition state 1 between binding site and the lowest energy minimum and the binding site binding mode 2. Also here, water present interaction, we did our job, computer analysis of the analysis that I told you, and it's really nice to show you that a binding rate is only 1 order of magnitude below, faster than, slower, sorry, than the experimental value. And we are computing the frequency as a function of the time. But if you do this with the logarithm, as it's supposed to be to understand, to compute the height of the barrier, you can understand in a logarithmic scale, these numbers are pretty similar, okay? So it's a very nice example to see that this method works. I think that since you want to have a break, or we can, I think that now we just see some applications. Do you want to have some question? I cannot hear you. Sorry. Okay, oh, yes.
Okay, so thank you. And about the funnel shape, It's kind of similar to docking grid in a term that you
the grid of docking, you mean?
yes, that you define an area that you direct the ligand to, or the direction of the funnel. But when the binding site is not known to you, how do you define how to place the funnel?
Yeah, in principle, you don't need to have precise information about the binding mode. Of course, you need to have some preliminary information about the location of the binding site in the protein structures. But it's different from the grid that you use for docking. Because, of course, you need to know the region of the protein, but you can also use the funnel in order to explore different binding sites of your protein. So you can, if you have a putative binding site A here, this point of your protein structure, another one here, you can apply two funnels, for instance, and check which one gives you the lowest energy binding pathway, the lowest energy binding free energy in that case. And funnel application, just a restriction of the phase space. You are not computing any grids, any kind of probes to estimate the fingerprints or affinity like docking. It's just you are saying, okay, I want to restrict my assembly here, and you can tune, of course, the amplitude of the cone. So the direct answer to your question is that you need just a preliminary and not so accurate information about the localization, the position of the binding site in your protein structure, nothing more. But forget about any accurate information of the binding mode of your ligand. You don't care. Okay.
So you actually recovered Vota's hyperdynamics, didn't you, with the slow deposition of Gaussians?
So what, please?
Art Vota's hyperdynamics.
Yeah.
You recover that limit when you deposit the Gaussians slowly.
Yeah.
Right, so that in principle can give you the acceleration factor and everything from
Yeah,
that.
sure.
Yeah.
Totally agree. Yeah. Hyperdynamics is it's a similar approach to that one. So that's one, yeah. Yeah, you're right. Yeah. Perfect. Other?
No more questions?
Okay, so let's go on with some application before the lunch break. So this is a very nice example in which we apply two structurally similar ligands. This is catechol and methyl catechol to peroxyredoxin 5. I don't want to get into biological detail because otherwise we don't have time. The most important thing is we were able to discriminate between the two ligands that have a difference of only 1 kilocalorie per mole, a difference in binding free energy, and we were able to see that after our calculation converged, so you can compute, you have to compute, I would say, the binding free energy, as you will see this afternoon, the binding free energy is a function of the sublimation time, and you should converge to a certain value, okay? While this estimate converge, you should continue observing the sampling of the bound state. This is a practical way to check the convergence of the calculation. Anyway, we can estimate the difference in binding free energy between these two very similar ligands, and we also did this in collaboration with a French NMR group of Lansen in Lyon. They measured the dissociation constant based on the NMR chemical shift. And when we compare the binding free energy of Funnel-Metadynamics with NMR, you can see the agreement for the catechol is very impressive, and the methyl, 4-methyl catechol, just difference of 1 kilocalorie per mole. What does it mean? This means two things for you guys as students. First of all, an accurate method, whatever it is, if you know the binding mode, FMAP, Funnel-Metadynamics, whatever, it's able to discriminate between very subtle changes between in the structure of a ligand. In this case, the fact that the methyl catechol has a lower, so more stronger binder because of the lower binding free energy is due to the fact that methyl group is able to interact with the hydrophobic pocket made by phenylalanine residue and isoleucine residue. So this is another advice for you. Always check the analytical mathematical results with something that is chemically sound. Go do a visualization of your results in order to understand, I'm able to rationalize this number. And this you can see here. This hydrophobic interaction rationalizes the difference. The other message is that I told you that there is force field inaccuracy. So of course 1 kilocalorie of difference is not reliable in terms of force field accuracy. But we are studying the same system with very similar compounds. So the inaccuracy of the sources, of course, is, can be neglected because it's average between these two systems, okay? So another example, another potential application of the method, you can apply this to study different ligands, as I showed you before, towards one target, or you can apply, you can study the binding of the same ligand, like in this case, to different forms of your target. It means the wild type, the mutant 1, mutant 2, whatever you want, and see how the free energy landscape of the binding change in order to understand if mutation affects or not that binding mode or the other binding modes, and so on and so forth. This is something we did in collaboration with Carla Morteni in London, and we studied the GABA binding to the ligand gate ion channel. And going on with the application of the method, we can see that we can also use, I don't know why it's not working, okay, on DNA G quadruplex binding in this case, on this PNS paper. This is nice, this PNS paper, because we compute the binding free energy in this case. It's converged, as you can see, in the bound state of this ligand towards this binding site, external solvent exposed binding site of G quadruplex. And we were able also to use this our weighted scheme to compute the contribution of waters. So to understand that the binding can be also favored by the presence of water here, it is able to interplay, makes an interplay loop between the DNA and the ligand. And we compute the binding free energy, and then also in the same paper we performed some Fourier sequential experiments, and we computed the binding free energy for the same ligand was in a good agreement with the theoretical data. And so also for DNA ligand binding study, you can also use to study allosteric binding site, like in this case, in the allosteric pocket for this GPCR, this purine receptor, P2Y1, in which we study how the ligand, this one, diffuse in the membrane and then recover the X-ray structure. Unfortunately, this is white, but the white is their X-ray, and the purple one is that one that was predicted by the Funnel-Metadynamics simulations. It's another very interesting example of this kind of study. And a recent one just accepted on GCDC this month is the application of, is the study of the binding to this allosteric site of this ligand in the HSP90, H-shock protein 90. And it's important because this is supposed to be the ligand binding that has some allosteric network connection to the 8B binding site where the protein makes the action. And indeed, if we found the convergence of our calculations and the different binding modes that we found during here, we can compute also dynamic cross-correlation, which we can find how the different minima found in our calculation induce conformational change even 10, 20 angstrom away from the ligand binding. The ligand binds here, and we can observe effect on the other chain. This is a dimer on the other chain, also very far from the binding site. Please. The funnel, you mean? Well, because this was already known as allosteric binding site. It was known by literature. Of course, it was not known the binding mode. It was known that it was an allosteric inhibitor. It was an allosteric ligand of this protein, and we just place a funnel here with a large cross-section in order to explore very well the binding site. And once we get the final binding mode, we can compute this dynamic cross-correlation matrix. Okay. Okay. Let me conclude my talk with the last sample because I think I'm running out of time. No, not yet, actually. Okay, so I can continue. Okay, I thought it was a. So, an important point, because I show you that you can use this kind of calculation to estimate the ligand protein, ligand DNA binding affinity, compute the rates. Also, you can use drug-like compounds. So you have many a broad range of applications, I may say. But still, you may ask me, okay, but if I have a very large conformational change in my protein, how I can take this into account? So in other words, what if we have large protein conformational motion? In other words, a large configuration entropy contribution to my binding free energy? Yeah, it's much more difficult, okay? And I can show you that this is possible, even though it's not simple, I must say. Like in the case of adenosine deaminase, an important enzyme for the metabolism of adenosine in the central nervous system, so it's involved in many neurodegenerative pathologies, but forget about that. And in 2012, on PNS, we published this paper, Sampling Protein Motion Solvent Effect during ligand binding, in which adenosine deaminase was found by X-ray studies to have two types of states, an open one in which we have a binding pocket that can be described by 4 different binding interaction points, and a closer one in which we have just a reduced size of the pocket. So this is a large scale motion of the protein in making this helix displacement during its action. So what you can do is that at that time, like you, I worked as a medicinal chemist. So I have some experimental collaborator that came to me and said, okay, I have this new potent ligand with 4.25 nanomolar activity towards this target, but we don't know anything. We could just discover in our lab. Could you please help us to rationalize the structural activity relationship with data in order to improve the activity of this ligand towards this target? I tried, as most of you. I did some docking calculation. I collect the X-ray structure, the closed and the open. I did my calculation. I was already, I would say, a good medicinal chemistry student, so I thought, well, let me also include some crystal waters because maybe this may help in guiding me, in finding the right binding mode. But in the end, I was not able to find a very convincing binding mode results. So even including crystal waters using closed and open states, I was not able to have a very clear convergent data by docking, and the binding modes were not in agreement with the SAR data that my collaborator have. So using the binding mode coming from docking, I was not able to explain the experimental data. So I had to take another route. And docking failed. Docking failed. Why? Docking failed. Why? Because docking does not take into account explicitly the waters. Could be one of the reasons why docking fails. Docking may fail because the product flexibility is not taken into account. So such flexibility is not taken properly into account. There are some exceptions. We can include some rotamers, but still at the cost of the convergence time, the scoring function, and so on and so forth. I don't want to enter into these details. We already attended brilliant talks about that. Large protein movement also play an important role. So in the case of adenosine deaminase, in which we have this motion of the helixes, this is completely not taken into account in our docking studies. So the solution is to use some techniques that allow us to take into account explicitly the waters and also the product flexibility. And what we did in this case, we used the path collective variables. This is nice work, that was a nice approach introduced by Davide Branduardi in 2007, followed by Massimo Bonomi, and originally also developed by Rene van den Eyden in 2005. So this means that you can do a dimensionality reduction of your system. Suppose you have many degrees of freedom, an helix that open and close with many contacts. You try to converge, you try to collect all this motion in a few degrees of freedom. And this is the path CV S and zeta. Basically, using this formula, what you get, you define a starting state A and a final state B, and you can describe with a discrete number of frames in the matrix of a distance, or a contact map, whatever you want, the motion of your system from state A to state B. In doing so, you are able to sample, if you do your meta-dynamics, for instance, or any enhanced sampling in this dimension, you can move your system from state A, suppose in our case closed state of adenosine deaminase, to the B state, which is the open state. In addition, you can add this orthogonal collective variable, the zeta, which allows you, with this formulation here, to explore all the parallel dimension of your path. In doing so, you are sure that even though you commit any mistakes in building your original path from A to B, you are able to find new path exploring some parallel dimension, okay, orthogonal dimension, and allows to find also the lowest energy path going from A to B that can be even different from the original path that you set. So you are exploring, in this case, 2 dimensions, but taking into account many degrees of freedom. And again, what happened, looking back to our original picture, state A, state B, you can describe these different frames. You can use also linear interpolation wherever you want as a starting path, because then you can use the zeta collective variables that allows you also to go farther from the reference path and find the lowest energy pathway, like in this case, for instance, and you can apply this to many, many systems. It's of course, it's time demanding because you have to align the 2 metrics, but it's very, very useful when you need to describe a large-scale motion, like in this case. Indeed, this is a simulation in which we applied the path corrective variable in order to simulate the opening and the closure of the helix of the adenosine deaminase, and the ligand explore the binding site, because in this case we have not only the path corrective variables, but we have also the distance between the ligand and the protein, and the torsion of the orientation of the ligand with respect to the protein. In doing so, you can explore all the possible binding modes in your protein during the action of your protein, in this case, or in this case of your enzyme, with the motion of the helix. What happens in the end, that once I identify the lowest energy binding mode, and I compare my metadynamics conformation of my system with respect to the X-ray structure, you can see that the closed orange one and the green one is the open X-ray. My metadynamic simulation, my metadynamic structure is still more open than the X-ray one. And this may explain the failure of my docking, because I was just using the X-ray structure before. So there was not enough space to host the long alkyl chain on my ligand. And in addition, if we look at the binding mode, we can find that there is also a water molecule here that plays an important interacting role between this aspartate 90 and my ligand. So this means that, as you can see here, this means that it was necessary to take into account the large-scale motion of the protein to get a reliable estimate of the protein binding, or the ligand binding mode. You can also, when you do this kind of calculation, you can also recompute the Boltzmann probability distribution for CVs different for those that you have biased during your simulation, using one of the reweighting formats that are available in literature. And what I did here, using the description of this, the interfacial water takes into account the coordination of water molecules between the ligand and the protein, you are able to recompute the free energy surface as a function of the collective variable that you compute using a reweighting scheme, and another collective variable. You can find that when the ligand is bound, a lower value of the distance, the contribution of water is determinant in order to have the final binding mode. So the water plays an important role in this case, and you can check using this kind of calculations also the contribution. Okay, now I get the binding mode, but it's theoretical calculation. Experimentalists want to support you, wants evidence, experimental evidence to support your theoretical study, particularly if you go on journals like PNAS. So I found that was released, this ligand was different from mine, but was a ligand that occupies similarly the pocket like the binding mode that I discovered in my calculation, because with many common points, like the interaction with the water molecules between this oxidized group here and the aspartate here. So it was a good overlap in order to convince the referee that my binding mode is reliable. Not only, I also did, as I told you, so to complete, to go back to my previous message, I don't know, today it's the day of crash of a keynote. Okay, I also convinced the referee with some a posteriori dock. As I told you, everything depends on the task of your study. I have to study also the other ligands, because I told you the collaborators gave me a list of ligands, active and inactive towards this target. And in principle, I could do all the Funnel-Metadynamics simulation, whatever I wanted, but it was not convenient. And once I have the protein structure and I have a congeneric series of ligands, I may go to docking. It's faster. And what I did posteriori docking, but using the protein conformation that I found using metadynamics. Shorter, smarter. In the end, the collaborators didn't want to wait. They want a very quick results. And indeed, I found, doing the redocking, you see how comparing metadynamics pose at docking and conserving the waters that I found in my calculation, I was able to retrieve as the best docking pose my ligand binding mode. And once I have it, well, it would be easy to do the docking for all the other molecules and try to explain the structure-activity relationship data that in many cases you have in your hands in order to identify which molecules are more potent than others. And we could explain why the alkyl chain allows to increase the activity, because reach this hydrophobic pocket here and allows to increase a little bit the activity with respect to the shorter chain. Okay? And this is a very nice example in my opinion. Metadynamics is predictive. Well, if you do things, as I told you, if you do things in the accurate way, for all the methods, you can get reliable estimates in free energy, reliable structures. So the message for you is to try to use the method at its best. Not just simply tutorial, forget about the theory. So be accurate, okay? Be accurate. And indeed, metadynamics applied to the folding of DNA. We found this intermediate structure here that we call G-triplex. And when we cut this oligonucleotide of these residues in order to see if this structure exists in reality, this was predicted in Angevante in 2013. And indeed, 1 year later, the NMA structure was perfectly identical, overlapping to the structure that we found in our calculation. So you can do a good prediction if you do a good calculation. This is the message. And we don't have time to speak about Gauss-Gramer dynamics. I'm sorry, because I'm out of time. Let me just go fast. I would just to show you, we don't have time, just to show you some unpublished data that show you that you can also use, at a Gauss-Gramer level, this kind of approach to study the dimerization of two proteins in membrane plane. So the yellow beans are lipids, the black beans are cholesterol, and these are two GPCR protein, G-protein coupled receptors, that can interact, bind, and bind several times during your simulation, and you can get at the end your free energy landscape in order to identify the different dimer states of your protein in a membrane. If you want to have news about that, you can catch me, or you also ask Daniele, that was the person in charge of this in my lab when he was postdoc with me. Just let me conclude. Skip about that, about the protocol. Wait, I want to just make just some advertisement. We develop also this drug discovery tools that for you that do computational stuff may be useful. It was developed by Simone Aureli in my lab, just published on bioinformatics. It's a tool very simple actually. It's integrated in DMD, and it can be useful to analyze using DMD and using the same graphical user interface, both docking coming from Autodoc and molecular dynamics coming from whatever programs you prefer, Gromax, NumPy, or AMDER. And what you can compute the score using an energy score like those of that of Autodoc. You can cluster your poses. And the nice thing, you can plot the central mass of your ligand in the Cartesian space in order to understand if both the, for instance, a virtual screening protocol put the ligand in the same pocket to say, okay, here's the hot residues are here, but also to identify if your molecular dynamics simulation, the central mass of your ligand is concentrated into a specific part of your protein to understand if it's a local minimum or you can do many analysis, and also to compute the histograms of the most frequent neighboring residues that are interacting with your ligand to have a frequent occurrence of the interaction between the ligand and the protein to understand, okay, this interaction is more stable during my MD simulation or is found, most of the cases, screening 30,000, for instance, ligands. I always found that aspartate interacts with most of these ligands. This means that this is a good interacting point that is important to target for drug design. So if you want to have a look, you can just download for free this software on my website. There's the docking protocol and also the MD protocol. You can do that. And the protocol that we develop, Funnel-Metadynamics, also the Gauss-Gramer dynamics, are now in Improvement Nest. This is public repository for enhanced sample simulation. It was just published on Nature Methods this year. And if you go here free of charge, you can download protocol, input files, also the data that were used to publish this kind of results. So you can reproduce the data for my protocols, but also for many others, for all the Puma community. And we are, if I'm not wrong, it's 70 authors. So you have many, many protocols uploaded here, and many more will coming in the future. So with this, I think everything is done. So we have some Metaflix. It means that we have a collection of videos. You can have a look, have fun, whatever you want. Go on the YouTube channel, and you can see what has been done using this kind of method in the recent years. And let me just acknowledge my group. Without them, it's impossible to do this kind of reach this kind of results. Now, the group here, and particularly, I have to thank Stefano Ragnolo and Paolo Conflitti as the two guys that set up all the machines in the computer rooms. They did amazing work. They worked a lot, so really believe me, if you can do this school is mostly thanks to their technical help. Simone as well, doing some experimental stuff in Bellinzona, and other people part of my group that are here in Lugano, other are in Naples, with which I interact in the different projects. Some funding and postdoc position is available, so please just drop an email if any of you is interested in coming. And thank you all.
So now we have some just few minutes for questions, and please don't be shy. And
I'm one of the, I know that you're hungry, you want to go to have lunch, but I'm one of the co-organizers, so please ask whatever you want, also practical stuff, whatever. Of course, we can meet also later. There's one over there, but we also interact later in the practical session, of course, but you can ask whatever you want. Don't be shy.
Okay, thank you for your talk. And I have a question considering the when you were explaining the binding modes, there were 2 binding sites, and you said that 17% of the time it binds to one
Binding pathway.
binding pathway.
One binding mode, 2 different binding pathways.
Ah, okay, okay.
Yes.
Then
I already solved your question.
yeah, okay.
Okay.
Okay, then maybe just the follow-up. If you have 2 binding sites, how do you implement the cooperativity of these 2 binding sites?
Well, your question is okay?
Yeah.
Finish? Okay, your question touches at different points because I want just to rewind a little bit. So, the first goal is to find the binding mode, okay? And once you have the binding mode, the point is that if you have the thermodynamics, okay, the binding constant, then you may be interested in understanding the kinetics. So when you have the ligand in the binding mode, especially when it's a barred binding site, you may have multiple different pathways, but you have to identify that one that affects your rate. So the rate determines pathway, first question. So one binding mode, different pathways, just trying to find the slowest, okay? Okay. Not slowest, I say better. The rate limit is so that defines the binding rate. Then your question is, if you have 2 binding sites, not binding mode, define these 2 currently. So this means one binding site in a region of protein, another binds another region. Yes, in this case, you have many things to check. First of all, is the allosteric communication between them. So it's supposed to bind to both sides that communicate allosterically, as we did for the JCTC paper, doing some dynamic cross correlation, whatever you want to understand if there are kind of communication between the 2. If you just want to investigate which of the 2 binding sites is the preferred one, you can perform 2 simulations, 2 Funnel-Metadynamics simulations, and to see where you find the lowest energy binding pathway and the lowest energy binding mode. But if you know that you have a stoichiometry, for instance, or 2 ligands per molecule, so you have one there and one the others, you have to check, you have to do this at the same time and to check how the binding of ones affect the others and vice versa. It's not easy, but you can do technically, but it's not easy. It's very nice. Maybe G quadruplex is an example. There are examples, but generally the allosteric binding site is targeted by a ligand different from that target the binding site. But still you can do. Also, if you have 2 different ligands, you can study the interaction. But so I'm not so sure if you understood what I said. Simultaneously, but you have also to check the communication, the allosteric communication between them, because you may have this effect, even long range. Even if these are not visually intuitive, you check in the trajectory, you don't see that. You have to do some kind of accurate evaluation of the communication between them. The cooperative, right? Please have a look to this GCDC paper we published with Giorgio Colombo. It's a very nice example. This RMSF analysis, dynamic cross correlation, do many analysis mapping to understand if there is a communication between them. Covariance, you can also try to compute.
But if we perform 2 different simulations on the same system and on 2 different tasks, are our results comparable in terms of binding affinity?
Sorry, I don't get the point about the 2 tasks. I understand.
You have just said that in the case of quadruplex, we can perform 2 Funnel-Metadynamics simulations with the funnel on the bottom and on the top of the quadruplex. And then
independent simulations. You take your system, simulation A, simulation B.
We can't compare.
We can't. Why?
We can't compare the 2 values.
Why? The same system, the same force field, and you have an accurate method that you can apply umbrella same wherever you want. In the end, you have the comparison. You can identify not only the lowest energy pathway, but you can also compare the binding affinity because you converge in the bound state. So you have the same ligand, the same reference point in the bound state. So the binding site that allows you to get the lowest energy binding mode is the most probable. So if you find another, so it's a matter of quantification. You have one binding mode is, let me say, minus 12 kilocalories per mole. The other one is minus 6. This means that both exist, but of course, in most of the time, you are in the lowest energy binding mode. Okay? Sorry, I want to just complete this question. If you also read the review of Copland that I mentioned, it's very nice because touched a little bit both the question, because he said when the ligand is in the tissue, it just reached the tissue, okay, or the district, the cell, where is the target. Well, the ligand is not there as we suppose it is, just in the bulk, but it starts to interact with the surface. So the fact that the ligands, before going to the final binding site, can interact with the protein is not an artifact of the simulation. It could be really how the mechanism works. It's there, it touches, and then get in. In addition, we are just simulating one ligand and one protein. In the reality, we have some concentration there. So we have more ligands, more protein. So you may have some ligands that are exploring the surface and others that come. So it's more complex, of course. So keep this in mind when you approach this kind of studies. Huh?
How many collective variables had to be defined to find the binding pose of the one in the example? I mean, like one collective variable could be like a distance, another could be one dihedral. Was it enough, or should there be another dihedral? Like
yeah, in most of the cases, it depends. Of course, the experience works an important role. In most of the cases, if the protein does not undergo large major conformational change, the distance that describes the distance between the central mass of ligand at the binding site and the torsion CV that describes a different orientation is sufficient. Okay, but if you have some additional, you can notice this, because suppose you run your first simulation using distance at torsion CV, and you do not converge, because as I told you, Funnel-Metadynamics is self-diagnostic. If you do not converge, this means that your CVs are not correct. It just gets stuck. You see that your system is there, never leaves this, the system never leaves this basing. This means that you are adding there, but it's some hidden barrier that you are not taking into account properly. So go back, reset, and check. One could be the motion of the ligand, a conformational mode like in the adenosine deaminase case. Another could be the desolvation of the pocket. This is an important issue, because in some systems you have some channel. So when the ligand enters, the water can exit from an exit channel. In other cases, you have the waters there, and you need to desolvate the protein. This may be a slow motion, because when the ligand enters, it should desolvate the ligands, but also the binding pockets should be desolvated. And this should be something that you can be taken into account with the explicit CV. If you notice this kind of behavior, you can use the distance torsion and a third CV that can allow you to take into account this solvation effect. I show you also the VAC Funnel-Metadynamics application of JCDC just published this year. And in that case, you can identify, you can define different descriptors. Water, so solvation effect for the ligand, solvation for the pockets, and whatever you think it's important for your system, that you can obtain also by preliminary molecular dynamics simulation, doing a principal component analysis. You get the slow motion, do some essential dynamics, and include this as degrees of freedom. Something you can do if your system requires this kind of more rigorous or more, I would say, more sophisticated and more challenging, of course, approach.
Maybe we can just stop here.
Yeah.
Vittorio is here, so if you have more questions, maybe we have time to discuss with Vittorio about Funnel-Metadynamics. So now it's time to have lunch. So see you in the other building at 2:00 p.m. for the practical session.
Thank you.